Tonight we're going to explore one of the oldest questions humanity has ever asked. Not how the universe began, not how it will end, but whether somewhere beyond the darkness between the stars, someone else is asking the same question. Imagine standing alone beneath a clear night sky. The stars stretch from horizon to horizon. Thousands of points of light shimmer above you. Behind them lie countless more invisible to the naked eye. Entire galaxies hide beyond those stars. Beyond those galaxies lie more galaxies still, a universe so large that numbers begin to lose meaning. A universe containing hundreds of billions of stars in our galaxy alone. A universe containing hundreds of billions of galaxies. A universe old enough for civilizations to rise and fall long before Earth even formed. And yet, despite all of this scale, all of this time, all of these opportunities for life to emerge, the universe appears silent. No confirmed signals, no confirmed visitors, no confirmed evidence that another intelligent civilization exists. Only silence. At first glance, this silence seems ordinary. After all, perhaps we simply have not looked long enough. Perhaps our instruments are still primitive. Perhaps the distances are too large. But as the decades passed, a strange realization began to emerge. The silence itself was becoming a mystery, because the more astronomers learned about the universe, the less empty it appeared. In the early 20th century, humanity knew almost nothing about planets beyond our solar system. The stars were distant lights. Interesting, perhaps. Beautiful, certainly, but largely unknown. Many scientists wondered whether planets even existed around other stars. There was no proof, no evidence, only speculation. Then the discoveries began, slowly at first, then faster, then so quickly that entire catalogues had to be rewritten. Astronomers discovered that planets were not rare exceptions. They appeared to be common, very common. Worlds larger than Jupiter, worlds smaller than Earth, worlds orbiting red stars, worlds orbiting binary stars, worlds covered in oceans, worlds scorched by their suns, worlds drifting through space without any star at all. What once seemed extraordinary suddenly looked ordinary. The galaxy appeared filled with planets, and if planets were common, perhaps life was common as well. The question became unavoidable. If nature creates planets everywhere, why would it create life only once? The night sky began to look different. Each star was no longer merely a distant sum. Each became a possibility, a potential home, a potential civilization, a potential history unfolding beyond human awareness. Imagine shrinking yourself down to the scale of a city. Now imagine Earth becoming the size of a continent. Then imagine the solar system becoming an entire planet. Even at that scale, the nearest star would still be thousands of kilometers away. The distances remained enormous, but the number of opportunities was even larger. Throughout the galaxy, there are stars older than the Sun by billions of years. Some formed long before Earth existed. Some may have hosted habitable planets, while our world was still molten rock. If intelligent life emerged there, those civilizations could possess advantages measured not in decades or centuries, but in geological ages. Imagine a society with a 1,000-year head start. Now imagine one with 1,000,000 years. Now imagine one with 100 million. Human civilization, by comparison, occupies only the thinnest fraction of cosmic history. Recorded history spans roughly 5,000 years. Agriculture appeared around 10,000 years ago. Industrial civilization emerged only a few centuries ago. Radio technology arrived little more than a century ago. On cosmic timescales, humanity has barely begun speaking. And yet the universe had billions of years to produce others. This realization transformed the question. The mystery was no longer whether life could exist elsewhere. The mystery became why we had not found any sign of it. Or, perhaps more troublingly, why it had not found us. Imagine a civilization millions of years older than ours. Its technologies would likely appear incomprehensible. Its machines could operate on scales beyond modern engineering. Its influence might extend across entire star systems. Given enough time, perhaps even across regions of a galaxy. Such possibilities inspired generations of scientists, writers, engineers, and dreamers. The future suddenly appeared larger, not merely because humanity might travel among the stars one day, but because others might already have done so. Entire futures seemed possible. Galactic civilizations, interstellar networks, ancient cultures spanning thousands of worlds, histories older than mountains, knowledge accumulated across millions of years. The possibilities felt limitless. Yet every telescope continued reporting the same result. Nothing. No unmistakable evidence, no undeniable confirmation, no cosmic greeting waiting to be discovered. The universe continued offering stars, planets, nebulae, galaxies, but never the one thing many expected to find, eventually, another intelligence. For a time, scientists remained optimistic. Perhaps the search had only just begun. After all, humanity had been listening for only a few decades. The galaxy was vast. Patience seemed reasonable, but the deeper researchers looked, the stranger the silence became. Every new discovery increased the odds that life should exist somewhere. Every new exoplanet strengthened the case. Every new understanding of chemistry suggested that the ingredients of biology were widespread throughout the cosmos. Carbon existed everywhere. Water appeared common. Organic molecules emerged in unexpected places. The universe seemed eager to create the building blocks of life. And yet evidence of intelligent civilizations remained absent. The contradiction grew. More opportunities, more planets, more time, more possibilities, the same silence. By the beginning of the 21st century, the question had evolved into something much larger than a search for aliens. It became a question about the structure of reality itself. Perhaps intelligent life was extraordinarily rare. Perhaps civilizations inevitably destroyed themselves. Perhaps the distances between stars were insurmountable. Perhaps communication was impossible. Or perhaps something deeper was happening, a possibility far more unsettling. What if the universe itself was built in a way that prevented civilizations from finding one another, not intentionally? Not as a design, but as a consequence of the very laws that govern space, time, energy, and information. A kind of cosmic isolation hidden within the architecture of reality. An invisible barrier not created by distance alone. A barrier woven into the fabric of the universe itself. And if that were true, then the silence above us was not merely an absence, it was a clue. A clue pointing toward one of the greatest challenges any civilization could ever face. Not surviving, not expanding, not mastering technology, but overcoming a universe that seems determined to keep every intelligent species separated from every other. To understand whether that is true, we first need to understand the scale of the opportunity itself. Because before we can explain the silence, we must answer an even larger question. In a galaxy containing hundreds of billions of stars, how many chances has life actually had to emerge? And could the numbers themselves be hiding the first piece of the mystery? The question seems simple. How many opportunities has the universe had to create intelligent life? Yet hidden inside that question is a number so large that the human mind struggles to grasp it. Not because the mathematics are difficult, but because our instincts evolved on a single planet. We understand villages, cities, countries, perhaps even continents. But the universe operates on scales that make entire civilizations appear microscopic. To appreciate the mystery of the silence, we must first appreciate the scale of the opportunity. Imagine standing on a coastline. Every grain of sand beneath your feet represents a star. Not a planet, not a solar system, a star. A single sun. At first the beach seems vast. Then imagine every grain possessing its own collection of worlds. Some barren, some frozen, some consumed by fire, and perhaps a few capable of supporting life. Now imagine that coastline extending around an entire planet, then across thousands of planets. Only then do we begin approaching the number of stars scattered throughout the observable universe. The scale is difficult to visualize, because there is nothing comparable in everyday life. Humanity has built cities containing millions of people. The universe contains stars measured in numbers thousands of times greater than the number of humans who have ever lived. And for most of history, we had no idea whether those stars possess planets at all. That uncertainty shaped scientific thinking throughout the 20th century. If planets were rare, then perhaps life was rare. If life was rare, perhaps the silence was expected. But beginning in the 1990s, the picture changed dramatically. New instruments allowed astronomers to detect distant planets indirectly. Tiny motions, small dips in starlight, subtle clues revealing worlds otherwise invisible. At first, the discoveries were celebrated individually. Each new planet felt extraordinary. Each announcement became global news. Then, something remarkable happened. The discoveries stopped being unusual. They became routine. Hundreds of planets, then thousands. Then thousands more. Every year the catalogues expanded. The universe seemed filled with worlds. Scientists soon reached a startling conclusion. Planets appear to be one of the most common products of star formation. Nature does not create stars in isolation. It creates systems, families of worlds, entire architectures of planets circling suns throughout the galaxy. The implications were profound. For centuries, humanity had imagined itself living in a special place, a rare place, perhaps even a unique place. Now, the evidence pointed elsewhere. The universe appeared astonishingly fertile. Everywhere astronomers looked, they found opportunities. Rocky planets, ocean worlds, super-Earths, moons larger than planets, systems containing dozens of worlds, solar systems unlike anything previously imagined. The night sky transformed from a collection of stars into a map of possibilities. Every discovery made the silence more difficult to explain. Then another realization emerged. Many stars are older than the Sun, much older. Our Sun formed approximately 4.6 billion years ago, yet countless stars existed long before it. Some are billions of years older. This means potential habitable planets may have existed while Earth itself was still forming. Entire evolutionary histories could have unfolded elsewhere before life appeared in Earth's oceans. Imagine rewinding Earth's history. Back before humanity. Back before mammals. Back before dinosaurs. Back before complex life. Back before multicellular organisms. For most of Earth's existence, intelligent observers did not exist. Life emerged quickly. Intelligence emerged slowly, very slowly. Nearly 4 billion years passed between the first simple organisms and a technological civilization capable of radio communication. That timescale matters, because if intelligence requires billions of years to emerge, then older planetary systems gain enormous advantages. A world only 1 billion years older than Earth possesses an almost unimaginable head start. A civilization emerging there could be older than human civilization by a factor greater than all of recorded history. A civilization emerging several billion years earlier could possess a developmental advantage difficult even to describe. The comparison would not resemble two neighboring countries. It might resemble comparing modern humanity to prehistoric ancestors separated by entire eras of evolution. This realization intensified the mystery, because the universe has not merely provided many opportunities, it has provided opportunities spread across immense spans of time. Life elsewhere would not necessarily be our contemporary. Some civilizations could be younger, some older, some vastly older. The galaxy itself becomes a timeline, a vast landscape containing worlds at different stages of development. Some may still be lifeless. Some may host primitive ecosystems. Some may possess intelligent beings just beginning to ask questions about the stars. And some may have advanced beyond anything humanity currently imagines, at least in theory. The numbers seem overwhelming. Consider our own galaxy. The Milky Way contains hundreds of billions of stars. Even if only a tiny fraction possess habitable planets, the result remains enormous. Even if life emerges rarely, there may still be countless opportunities. Even if intelligence develops only occasionally, the galaxy has had billions of years to experiment. The odds begin to feel less like a lottery and more like inevitability. This is where the mystery becomes uncomfortable, because intuition starts working against us. If opportunities are abundant, then absence becomes harder to explain. Imagine entering a city containing millions of homes. Every light is turned on. Every street appears occupied. Yet you never encounter a single person. Eventually you stop asking where people are. You begin asking whether something is wrong with your assumptions. The same shift occurred in astronomy. The question slowly changed. Scientists were no longer asking whether life might exist elsewhere. Increasingly they were asking why evidence remained elusive. why no unmistakable signs appeared, why the universe seemed biologically promising, yet technologically silent. And this is where a dangerous assumption began to reveal itself. Human beings naturally think that if intelligence emerges, it spreads. After all, our own species crossed oceans, wrapped continents, connected the planet, built global communication networks. Expansion appears natural. Exploration appears inevitable. But is that actually true on cosmic scales? A civilization may master its world, then its solar system, then perhaps nearby stars. Yet every step becomes harder. Every expansion requires more energy, more time, more coordination, more resources. The universe rewards growth up to a point. Beyond that point, growth encounters barriers. The deeper scientists examined the problem, the more those barriers appeared everywhere. Distance, energy, communication, time, survival. Each challenge multiplied the next, and suddenly a new possibility emerged. Perhaps civilizations are not rare. Perhaps expansion is. Perhaps intelligence appears throughout the galaxy while remaining confined to isolated islands, separated by impossible oceans of space. The image is striking. Not a bustling galactic community, not a connected civilization spanning stars, but countless isolated worlds, each developing independently, each wondering whether others exist, each trapped behind distances too great to cross. At first, this explanation seems reasonable, yet it creates another problem, because even if civilizations never travel physically, communication should still be possible. A signal travels far more easily than a spacecraft. A message requires less energy than migration. A civilization separated by hundreds of light years might still announce its presence. The stars do not need roads if information can travel between them, and that observation leads directly to the next stage of the mystery, because once humanity began calculating the true distances between stars, researchers discovered something unexpected. The problem was not merely that the galaxy was large. The problem was that space itself behaved in ways that transformed distance into something far stranger, something more difficult, something capable of isolating entire civilizations even when they desperately wanted to be found. And at the center of that obstacle stood a universal speed limit that governs every message, every signal, every spacecraft, and every attempt to bridge the darkness between the stars. The speed of light. For most of human history, distance was an inconvenience, a difficult journey, a dangerous voyage, a barrier that demanded effort, patience, and courage. But distance was never truly absolute. Given enough time, people could cross mountains, cross deserts, cross oceans. Entire civilizations expanded because every frontier eventually yielded to technology. A river became a bridge. A sea became a shipping route. A continent became a railway network. Human history is in many ways the story of shrinking distance. Generation after generation discovered new methods of moving people, goods, and information faster than before. The world grew smaller. The horizons moved outward. And with every breakthrough came the assumption that future barriers would eventually fall as well. Then humanity looked toward the stars and encountered a different kind of distance entirely. Not a larger version of earthly distance, not a more challenging frontier. Something fundamentally different, something woven into the structure of reality itself. To understand why the universe may be built to keep civilizations apart, we must first understand the scale of the gulf separating even the nearest stars. Imagine standing on Earth and looking toward the moon. The distance seems enormous. The Apollo astronauts traveled nearly 400,000 kilometers to reach it. Even today, that journey remains one of humanity's greatest achievements. Now imagine repeating that trip. Again, and again, and again. Not 10 times, not 100 times, but roughly 10,000 times. Only then would you approach the distance separating Earth from the nearest star beyond our Sun. The comparison feels absurd because human intuition was never designed for interstellar scales. The nearest stellar neighbor, Proxima Centauri, lies approximately 4.24 light-years away. The number itself sounds manageable, 4.24, a small number. Yet, hidden behind those digits is a distance of more than 40 trillion kilometers, a figure so large that ordinary language begins to fail. Suppose you entered a modern passenger aircraft. Instead of flying across an ocean, you pointed the aircraft directly toward Proxima Centauri. You maintained cruising speed continuously. No maintenance, no fuel limitations, no delays. The journey would require tens of millions of years, longer than human civilization has existed, longer than modern humans have existed, long enough for entire species to evolve and disappear. And that is merely the nearest star. The Milky Way stretches across approximately 100,000 light years. Light itself requires 100,000 years to cross it. Imagine sending a message from one side of the galaxy to the other. The message would depart before the earliest pyramids were built. It would arrive long after modern civilization had transformed beyond recognition. This is where distance begins to become something more than geography. It becomes time. Every glance into space is also a glance into history. The moon appears as it existed slightly more than 1 second ago. The sun appears as it existed 8 minutes ago. A star 100 light years away appears as it existed 100 years ago. A galaxy 1,000,000 light years away appears as it existed 1,000,000 years ago. The universe does not allow us to see the present. It allows us to see only the past. Every observation becomes archaeology. Every telescope becomes a time machine. This fact creates an extraordinary complication. Suppose another civilization exists around a distant star. Suppose it developed radio technology exactly as humanity did. Suppose it broadcasts signals across space. What would we actually receive? Not the civilization as it exists now. We would receive evidence of what it was years ago, centuries ago, perhaps millennia ago. The farther away the civilization, the older the information. Distance transforms communication into historical reconstruction. A conversation becomes impossible. An exchange becomes delayed beyond comprehension. Imagine sending a text message and waiting 800 years for a reply, then waiting another 800 years to respond. Civilizations separated by interstellar distances do not merely face communication challenges, they face chronological isolation. Each lives inside its own version of time. The implications are profound. Even if intelligent life fills the galaxy, meaningful interaction becomes extraordinarily difficult. Two civilizations may exist simultaneously while remaining effectively disconnected, not because they lack technology, not because they lack curiosity, but because space itself separates their timelines, and this problem grows rapidly. A civilization located 1,000 light years away sees Earth as it appeared during the early Middle Ages. A civilization located 10,000 light years away sees a planet without modern science, without industry, without radio, without evidence that technological humanity exists at all. Likewise, when we observe them, we observe ancient history rather than present reality. The galaxy becomes a vast archive of delayed information, a place where everyone is looking backward. No one sees anyone else as they are, only as they were. This alone would make interstellar civilization difficult, but the universe imposes an even stricter limitation, because light does not merely travel quickly, it travels as quickly as anything can travel. According to everything modern physics has discovered, light is not simply fast. It is the ultimate speed limit. No message, no spacecraft, no information, no physical object can exceed it. This transforms distance from an engineering problem into a fundamental constraint. Humanity has repeatedly overcome technological barriers throughout history, but overcoming a law of nature is something entirely different. Engineers can improve machines. They cannot rewrite reality. Imagine a future civilization possessing technologies far beyond our own. Fusion reactors, artificial intelligence, planetary engineering, machines capable of reshaping entire worlds. Even such a civilization would still confront the same speed limit. Its greatest spacecraft would remain constrained by the structure of space-time itself. The universe grants astonishing possibilities, then places strict boundaries around them, and suddenly the silence begins to look less mysterious. Perhaps civilizations are separated not by ignorance, but by physics, not by unwillingness, but by geometry, not by lack of effort, but by the architecture of the cosmos. The stars are visible to one another, yet separated by intervals that transform communication into patience and travel into epochs. Imagine a family sending a probe toward another star. The launch becomes a historic achievement. Generations celebrate. Monuments are built. Songs are written. Then centuries pass. The original participants die. Their children die. Their grandchildren die. The mission continues. Long before arrival, the civilization that launched it may have changed completely. Perhaps the destination civilization changes as well. The journey becomes detached from the intentions that began it. Distance stretches not only space, but meaning. The farther one looks, the more civilization itself becomes difficult to preserve. A voyage lasting centuries raises questions that engineering alone cannot answer. How do cultures survive? How do institutions endure? How do memories persist? How does a society maintain purpose across timescales longer than recorded history? The challenge is no longer merely technological. It becomes biological, psychological, civilizational. And yet, despite all these difficulties, many scientists remained optimistic. Distance was immense, but perhaps not insurmountable. Perhaps advanced civilizations could still communicate. Perhaps they could still explore. Perhaps they could still spread among the stars. The speed of light imposed limits, certainly, but humanity had overcome daunting obstacles before. Maybe there was a path forward. Maybe physics allowed solutions not yet imagined. Maybe the silence had another explanation. Then researchers began calculating the energy required to truly bridge interstellar space, and they discovered something unexpected. Distance was not the only problem. In many ways, it was not even the largest one, because even if civilizations accepted journeys lasting centuries, and messages requiring generations, another obstacle stood waiting. An obstacle measured not in kilometers, not in years, but in energy itself. And once that calculation entered the story, the universe appeared even less welcoming than before. Distance is easy to imagine. Energy is not. Most people can picture a journey, a road stretching across a continent, a ship crossing an ocean, a spacecraft moving through darkness toward a distant star. But hidden beneath every journey lies a question that ultimately determines whether the journey can happen at all. Where does the energy come from? Human history has always been shaped by answers to that question. Ancient civilizations depended on muscles, human muscles, animal muscles. The amount of work available to society was limited by the number of bodies capable of performing it. Then came water wheels, windmills, coal, oil, electricity, nuclear power. Each breakthrough unlocked larger possibilities. Entire eras of civilization emerged from new ways of controlling energy. Cities expanded. Industries multiplied, transportation accelerated, technology advanced. At every stage, humanity gained access to larger reservoirs of power. Yet the distances between stars introduced demands unlike anything civilization has ever encountered. To appreciate the scale of the challenge, imagine throwing a baseball. Now imagine throwing it hard enough that it never falls back to Earth. That requires extraordinary speed. Earth's gravity constantly pulls objects downward. Escaping that pull demands tremendous energy. Modern rockets achieve this only through enormous machines, consuming vast quantities of fuel. The rockets that carried astronauts to the moon were among the most powerful vehicles ever constructed. Their launch shook the ground. Their engines produced forces comparable to natural disasters, and yet on a cosmic scale those rockets were barely leaving home. Reaching orbit is difficult. Reaching the moon is harder. Reaching another planet is harder still. Reaching another star belongs to an entirely different category. Every increase in velocity requires more energy, and the relationship is unforgiving. Double the speed and the energy requirement grows dramatically. Push toward a significant fraction of light speed, and the numbers become almost incomprehensible. A spacecraft traveling at 10% of light speed would cross the distance to Proxima Centauri in roughly 40 years. For the first time, interstellar travel begins to sound practical. A human lifetime, a manageable mission. An extraordinary achievement perhaps, but not impossible. Then the energy calculations begin, and optimism encounters reality. Such a spacecraft would require kinetic energy comparable to the total energy consumption of entire civilizations. Not cities, not nations, civilizations. And that assumes a relatively small vehicle. Add life support systems, add shielding, Add habitats. Add redundancy. Add the countless necessities required for survival in deep space. The numbers climb rapidly. What initially appears to be an engineering challenge gradually transforms into an economic one. Then a planetary one, then a civilization-sized one. Imagine a future society deciding to send a starship carrying thousands of people. The vessel might be kilometers long, perhaps larger than modern cities, perhaps containing ecosystems, industries, schools, hospitals, and communities. An entire miniature world moving through interstellar darkness. The image is inspiring. It is also extraordinarily expensive in terms of energy. Before the first passenger boards, civilization must somehow accumulate the power needed to accelerate the vessel. Then more power to slow it down at the destination. The journey demands energy twice, once to depart, once to arrive. And throughout the voyage, systems must remain operational for decades or centuries. Every calculation points toward the same conclusion. Interstellar travel is not merely transportation. It is resource mobilization on a scale humanity has never attempted. The challenge becomes clearer when viewed from another perspective. Consider Earth itself. Every second our planet receives immense amounts of energy from the sun. The total is astonishing. More energy arrives in a single hour than humanity currently consumes in an entire year. Civilization survives beneath a continuous flood of stellar power, and yet even this abundance appears modest when compared to the requirements of widespread interstellar expansion. The universe is vast. Crossing it demands correspondingly vast resources. This realization led scientists toward a profound observation. Advanced civilizations might not be limited primarily by technology. They might be limited by energy. A society could possess extraordinary scientific knowledge. It could master automation, artificial intelligence, genetic engineering, planetary management, yet still remain confined by the practical realities of power generation, because every ambition ultimately becomes an energy problem. Building cities requires energy. Manufacturing machines requires energy. Maintaining populations requires energy. Communicating across interstellar distances requires energy. Traveling between stars requires enormous energy. The deeper researchers examined the issue, the more energy appeared as the hidden currency of civilization itself. Entire futures could be measured through access to power. This idea inspired a new way of thinking about intelligent life. Rather than classifying civilizations by culture or politics, some scientists began classifying them by energy consumption. How much power could a civilization control? How effectively could it harvest the resources of its environment? How large could it grow before encountering limits? The framework suggested that truly advanced societies might eventually harness the energy of entire planets, then perhaps entire solar systems, maybe even more. The concept was extraordinary, not because it described alien technology, but because it reframed civilization as a thermodynamic process. A civilization survives by accessing energy and using it to create order. Without energy, complexity collapses. With sufficient energy, complexity expands. The implication was profound. Perhaps intelligent life is common. Perhaps technological life is common. Yet perhaps very few civilizations ever acquire enough energy to become visible across interstellar distances. The universe may contain countless societies living beneath the threshold of detectability, advanced by local standards, invisible by galactic standards. Imagine standing on a distant world hundreds of light years away. You build cities. You develop science. You create art. You establish governments. You dream about the stars. From your perspective, civilization flourishes. Yet, to a distant observer, your entire planet remains almost impossible to detect. Your achievements vanish into cosmic background noise. The galaxy could contain many such worlds. Busy, complex, intelligent, yet hidden. Not because they choose secrecy, but because physics naturally conceals small civilizations inside enormous cosmic spaces. The realization is unsettling. Humanity often imagines advanced civilizations as gigantic and obvious, monumental engineering projects, immense structures, visible signatures spanning star systems. Yet perhaps most civilizations never reach that scale. Perhaps the energy barrier prevents them. Perhaps many remain forever confined to their home worlds. A collection of isolated islands scattered throughout the galaxy, each intelligent, each curious, each effectively alone. At first glance, this explanation appears satisfying. Distance creates obstacles. Energy creates limits. The silence begins to make sense. But a deeper problem soon emerged, because even if interstellar travel proves difficult, communication should still be easier. A radio signal requires vastly less energy than a starship. A civilization need not physically travel to announce its existence. It need only transmit. And humanity has already done exactly that. For more than a century, Earth has leaked radio emissions into space, television broadcasts, military radar, communications networks, a growing sphere of information expanding outward at light speed. Any sufficiently sensitive observer within that region could, in principle, detect evidence that humanity exists, which leads to a troubling question. If we can broadcast unintentionally after only a brief period of technological development, why has no one else done the same? Where are the signals? Where are the accidental transmissions? Where are the technological echoes of civilizations that should have emerged millions of years before us? The numbers suggest there should be many opportunities. Distance explains part of the mystery. Energy explains another. Yet neither seems sufficient. The silence remains. And as scientists continued searching for explanations, attention shifted toward a possibility even more unsettling. Perhaps civilizations are not failing because they cannot cross the stars. Perhaps they are disappearing before they ever get the chance. A possibility tied not to space, not to energy, but to time itself. Because a civilization does not need to reach another star to vanish. It merely needs to stop existing. And once researchers began comparing cosmic timescales with the lifespans of civilizations, the silence acquired an entirely new meaning. For a moment, imagine that intelligent life is common, not rare, not extraordinary, common. Across the galaxy, civilizations emerge wherever conditions allow. Oceans give rise to biology. Biology gives rise to intelligence. Intelligence gives rise to technology. Technology gives rise to astronomy. And eventually, on thousands or perhaps millions of worlds, someone looks upward and wonders whether they are alone. At first glance, this seems like the answer. The silence disappears. The galaxy becomes populated. The universe becomes alive. Yet an unexpected problem immediately appears. Existence alone is not enough. To find another civilization, both civilizations must exist at the same time. And suddenly the challenge becomes far more difficult, because the universe is not merely large. It is old, extraordinarily old. The observable universe is approximately 13.8 billion years old. Earth is about 4.5 billion years old. Modern technological civilization is barely more than a century old. The contrast is astonishing. Humanity's radio age occupies only a tiny fraction of cosmic history. If the entire history of the universe were compressed into a single year, our technological civilization would appear during the final seconds before midnight on December 31st. Everything we call modernity would occupy an almost invisible moment. This realization transforms the search for intelligent life. The problem is no longer simply finding civilizations. The problem becomes synchronization. Imagine walking into a vast library containing billions of books. Each book represents a civilization. Some begin early, some begin late. Some flourish for long periods. Others end quickly. Now imagine trying to find two books open to the same page at the same time. The task becomes surprisingly difficult. This is the challenge facing any search for extraterrestrial intelligence. The galaxy may contain countless histories, yet those histories must overlap if contact is ever to occur. A civilization that existed 50 million years ago cannot communicate with humanity today. Its signals may be gone. Its artifacts may have vanished. Its star may still shine, but its story could already be finished. Likewise, a civilization that will emerge 50 million years from now cannot hear us. We will belong to its ancient past. The universe may be filled with intelligence, separated not by distance, but by chronology. Entire civilizations may miss one another, simply because they arrive at different moments in cosmic history. This idea initially appeared speculative. Then scientists began examining Earth's own history, and the implications became difficult to ignore. Life emerged on Earth relatively early, yet for billions of years, nothing resembling technological intelligence appeared. The planet remained inhabited exclusively by simple organisms. Then more complex life emerged. Then animals. Then mammals. Then humans. The process required extraordinary amounts of time, not centuries, not millennia, billions of years. And even after intelligent humans appeared, technological civilization emerged only recently. The lesson was striking. Intelligence is not merely a product of biology. It is a product of timing. Countless events had to unfold in the correct sequence. Mass extinctions, climate shifts, evolutionary innovations, geological stability. Each contributed to the eventual appearance of a technological species. Change one event and the outcome might differ completely. Perhaps dinosaurs never disappear. Perhaps mammals never dominate. Perhaps intelligence follows an entirely different path. Or perhaps it never emerges at all. The deeper researchers examined Earth's history, the less inevitable humanity appeared. The path leading to civilization looked increasingly contingent, increasingly fragile, increasingly dependent on circumstances. And yet, even after civilization emerged, another question appeared. How long does a technological civilization actually last? This question is far more difficult than it seems, because humanity possesses only a sample size of one, our own civilization, and its technological phase has barely begun. We do not know whether technological societies typically endure for thousands of years, tens of thousands, millions, or only centuries. No data exists, only possibilities. Imagine a civilization developing radio communication. For a brief period, it becomes visible across interstellar space. Signals leak outward. Evidence of intelligence spreads into the galaxy. Then, something changes. Perhaps communication technologies evolve. Perhaps radio becomes obsolete. Perhaps more efficient systems emerge. The civilization remains alive, but becomes harder to detect. Its visibility window closes. To distant observers, it briefly appeared and then vanished. This possibility introduces a remarkable idea. Civilizations may not remain detectable for long. The period during which they can be discovered might represent only a tiny fraction of their total history. Humanity itself offers an intriguing example. For decades, powerful broadcast signals leaked into space. Television stations transmitted continuously. Radar systems illuminated the sky. Communications infrastructure produced detectable emissions. Today, many technologies are becoming more efficient. Signals are increasingly directed rather than broadcast. Networks use less power. Communication becomes harder to observe from a distance. Paradoxically, a more advanced civilization may appear quieter than a less advanced one. Progress may reduce visibility. This creates a strange consequence. The search for extraterrestrial intelligence depends not merely on the existence of civilizations, it depends on civilizations being detectable at the right time. A society might flourish for thousands of years while remaining effectively invisible. A brief technological phase might be the only period during which it announces its presence. Miss that window and the civilization disappears from observational reach. The problem becomes even more severe when considering existential risks. Every civilization faces dangers: natural disasters, resource depletion, environmental change, conflict, technological accidents, unknown threats. The details may differ across worlds, but vulnerability appears universal. Complex societies require stability. The larger they become, the more systems must function correctly. Energy networks, food production, infrastructure, governance, knowledge preservation. Failures can cascade. The challenge is not merely creating civilization, it is sustaining civilization across centuries, across millennia, across cosmic timescales. Imagine a civilization surviving for 10,000 years. By human standards, such longevity would be extraordinary, longer than recorded history, longer than most institutions can even imagine. Yet on galactic timescales, 10,000 years is almost nothing. Light itself travels only 10,000 light years during that interval. The Milky Way spans roughly 10 times farther. A civilization could flourish for 10 millennia and still leave only a limited footprint across the galaxy. The universe is patient. Civilizations may not be. And this observation led scientists toward a sobering possibility. Perhaps the silence is not evidence of absence. Perhaps it is evidence of brevity. Perhaps intelligent societies emerge frequently, Perhaps many achieve remarkable accomplishments. Perhaps many dream of the stars. Yet relatively few endure long enough to become significant galactic presences. The cosmos may be filled with beginnings, and remarkably few continuations. If this is true, then the search for extraterrestrial intelligence becomes something more profound than a scientific project. It becomes a study of survival. The question shifts again. Not, where is everybody? But, how long does anybody last? Because if civilizations routinely disappear before spreading among the stars, then distance and energy are only part of the story. The deeper obstacle may lie within civilization itself, its ability to endure, its ability to preserve knowledge, its ability to survive the countless challenges encountered across time. And this realization produced a dramatic shift in thinking. Instead of asking only how to find extraterrestrial civilizations, researchers began asking how a civilization might remain detectable for thousands, millions, or even billions of years. Could intelligence leave traces that outlast its creators? Could advanced societies build monuments visible across interstellar distances? Could engineering itself become a form of communication? These questions inspired a new generation of ideas. Ideas that moved beyond radio signals, beyond messages, beyond conversations. Ideas focused on something much larger. If civilizations could not easily talk across the stars, perhaps they could leave evidence in another form, not through words, but through structures. Structures so vast that the galaxy itself would notice them. And that possibility would lead humanity toward one of the most ambitious searches ever attempted. A search not for alien voices, but for alien engineering. By the middle of the 20th century, humanity found itself in a peculiar position. For the first time in history, our species possessed technology capable of listening to the cosmos, not merely observing stars, not merely mapping planets, listening. The distinction mattered. For thousands of years, astronomy had been a visual science. Human beings looked outward and interpreted what they saw. Constellations, planets, comets, galaxies. The universe revealed itself through light. Then, a new possibility emerged. What if intelligent civilizations were not visible at all? What if they were speaking? And what if the galaxy was already filled with conversations passing unnoticed through the darkness? The idea was revolutionary, not because it required exotic technology, but because it transformed the search for extraterrestrial intelligence into something practical. Instead of traveling to distant stars, humanity could simply listen. The concept seemed almost elegant. Radio waves travel at the speed of light. They cross enormous distances. They penetrate interstellar space efficiently. And most importantly, humanity itself had already begun producing them. If radio represented a natural stage of technological development, perhaps other civilizations would discover it as well. The reasoning appeared straightforward. A civilization invents science. Science leads to electricity. Electricity leads to communication. Communication produces radio. Radio leaks into space. Eventually, someone else hears it. Simple. Reasonable. Hopeful. Yet hidden within that optimism was an assumption that would later become increasingly difficult to defend. The assumption that technological progress follows similar paths everywhere. For the moment, however, researchers focused on the opportunity. The galaxy contained hundreds of billions of stars. Surely some fraction hosted intelligent life. Surely some fraction developed radio technology. Surely at least a few were transmitting. The only remaining challenge was finding them. In 1960, a young astronomer named Frank Drake decided to attempt exactly that. At the National Radio Astronomy Observatory in Green Bank, Drake launched an experiment that would become one of the most influential scientific searches ever undertaken. Known as Project Ozma, it was remarkably modest by modern standards. A single radio telescope, a small number of nearby stars, a relatively brief observation campaign. Yet its significance extended far beyond its technical capabilities. For the first time, humanity deliberately listened for another civilization. Imagine the atmosphere, a quiet control room, electronic equipment humming softly, scientists watching instruments, a giant radio dish pointed toward distant suns, nothing dramatic occurring on the surface. And yet, hidden within that silence, silence was an extraordinary possibility. At any moment a signal might arrive, not from Earth, not from nature, but from another intelligence. A message crossing interstellar space. Evidence that humanity was not alone. The anticipation was immense. The results were not. Project Ozma detected no confirmed alien transmissions. The universe remained silent. Yet the experiment changed everything, because it demonstrated that the search itself was possible. Listening could be done, and once a scientific field becomes possible, it tends to grow. Over the following decades, more telescopes joined the effort. More observation campaigns were organized. More frequencies were examined. The search expanded. New technologies increased sensitivity. Computers improved analysis. Researchers began exploring larger portions of the radio spectrum. The dream persisted. Somewhere in the data, perhaps a signal was waiting, and occasionally something strange would appear. An unexpected transmission, an unusual pattern, a mysterious event. For a brief moment, excitement would spread. Could this be it? Could humanity finally have found evidence of another civilization? Then the investigation would continue. Equipment malfunction, satellite interference, natural astrophysical sources, human error. Again and again, promising clues dissolved under scrutiny. The silence remained intact. Yet the search continued, because the logic remained compelling. If intelligent civilizations existed, radio communication seemed one of the most plausible ways to detect them. Then an unexpected complication emerged, not from astronomy, but from humanity itself. Researchers began examining how communication technologies were evolving on Earth. The results raised uncomfortable questions. When radio first appeared, broadcasts were powerful and widespread. Television stations transmitted in all directions. Radar systems flooded the sky with energy. Military networks generated detectable signatures. Earth became increasingly visible. For a period, humanity effectively announced its existence to nearby stars. But technological progress was changing that. Communications became more efficient. Signals became targeted rather than broadcast. Fiber optic networks replaced many wireless systems. Transmission power declined. Information moved through narrower channels. Paradoxically, technological advancement reduced detectability. A civilization might become more sophisticated, while simultaneously becoming harder to observe. This realization forced researchers to reconsider a crucial assumption. Perhaps advanced civilizations do not produce enormous radio signatures. Perhaps radio communication represents only a brief transitional phase. A momentary technological window. If so, the chances of detecting another society become dramatically smaller. Imagine two civilizations separated by thousands of light years. Each remains radio loud for only a few centuries before transitioning to quieter technologies. The overlap between those windows may never occur. Both civilizations exist. Both develop science. Both explore the cosmos. Yet neither ever hears the other. The silence becomes understandable without requiring loneliness. This was a profound shift. The search was no longer simply about finding signals. It became a problem of timing again. The same obstacle encountered earlier returned in a new form. Civilizations must exist simultaneously. Now they must also communicate in compatible ways simultaneously. The requirements become increasingly restrictive, and every restriction reduces the likelihood of contact. Yet another problem soon appeared. Radio signals weaken with distance rapidly. A transmission powerful enough to cross a few light years may become difficult to detect across hundreds. Across thousands, the challenge becomes severe. The galaxy is not merely large, it is noisy. Stars emit radiation. Galaxies generate background signals. Natural processes fill space with electromagnetic activity. Finding an artificial signal within that environment resembles searching for a whisper during a storm. The farther away the source, the harder the task becomes. Imagine standing on a mountain and trying to hear a single voice originating on another continent. The challenge approaches absurdity, and yet this is effectively what radio astronomers attempt on a cosmic scale. The remarkable part is not that success has been elusive. The remarkable part is that the search remains possible at all. Still, as decades passed, the absence of evidence accumulated. More stars were examined, more frequencies were monitored, more sophisticated techniques were deployed. The expected flood of alien transmissions never arrived. The galaxy remained frustratingly quiet, not completely silent. Nature produced plenty of signals: pulsars, quasars, nebulae, magnetic fields, supernova remnants. The cosmos was alive with activity. What it lacked was unmistakable technological activity. The distinction became increasingly important. Scientists were not searching for energy. They were searching for intention. Evidence that somewhere, someone had deliberately created a signal. Evidence that intelligence had left fingerprints on the universe. But perhaps some researchers began to wonder they were looking for the wrong fingerprints. Perhaps advanced civilizations do not communicate through radio. Perhaps they do not communicate at all. Or perhaps truly advanced societies become visible in a different way entirely. After all, every civilization requires energy, and enough energy leaves consequences. A species capable of harnessing the resources of an entire world, or even an entire star, might alter its environment in detectable ways, not through messages, not through broadcasts, but through engineering. Civilization-sized engineering. Structures so immense that they could be observed across interstellar distances. The idea was extraordinary. And unlike radio communication, it did not depend on timing. A signal lasts moments. A structure might endure for millennia, perhaps millions of years. If civilizations vanished, their monuments might remain. If their voices disappeared, their constructions might still be visible. For the first time, the search for extraterrestrial intelligence began moving beyond listening. Humanity would not merely search for conversations. It would search for evidence that entire star systems had been transformed, and that possibility would lead scientists toward one of the most ambitious concepts ever proposed: the idea that an advanced civilization might eventually surround a star itself. The idea began as a thought experiment, not a blueprint, not a prediction, a question. What would a civilization do if it never stopped growing? It is one of the most important questions in the search for intelligent life, because every civilization faces the same fundamental constraint: energy. No matter how advanced a society becomes, it must power its cities, its industries, its computers, its transportation systems, its scientific instruments, its communication networks. Complexity requires energy. Civilization requires energy. And growth demands even more. Human history can almost be read as a record of expanding access to power. Wood gave way to coal. Coal gave way to oil. Oil was joined by electricity. Nuclear energy followed. Each transition unlocked new possibilities. Entire industries emerged. Entire economies transformed. The pattern seemed obvious. If a civilization survives long enough, it continually seeks larger energy sources. But how far can that process continue? In 1960, while Project Ozma was beginning its search for radio signals, a young physicist named Freeman Dyson proposed a remarkable possibility. Dyson was not attempting to predict alien behavior. He was attempting to think logically about energy. Suppose a civilization continues advancing for thousands or millions of years. Eventually, planetary energy resources may become insufficient. At that point, the most obvious source of power would be the civilization's star. After all, stars generate staggering amounts of energy every second. Earth intercepts only a tiny fraction of the sun's output. The overwhelming majority radiates into space unused. To Dyson, this suggested an intriguing idea. An advanced civilization might construct vast infrastructures around its star in order to capture more of that energy, not necessarily a solid shell. Popular culture often imagines a rigid sphere completely enclosing a sun. Dyson himself envisioned something more practical: a swarm, millions, perhaps billions, of orbiting collectors, habitats, power stations, artificial worlds, a civilization gradually expanding outward until much of its star's energy became available for use. The image was extraordinary. Imagine looking up at a sky no longer dominated by a natural star. Instead, countless structures orbit in synchronized patterns, artificial habitats larger than nations, industrial complexes harvesting sunlight directly, entire populations living in orbit. The star remains at the center, that civilization has transformed the surrounding solar system into an engineered environment. A planetary civilization becomes a stellar civilization. For the search for extraterrestrial intelligence, the implications were profound. Such a structure would be difficult to hide, even across interstellar distances. A star, partially surrounded by immense collectors, would appear different. Its light would change. Its energy distribution would shift. Astronomers might detect the signature, not because the civilization wanted to be discovered, but because engineering on that scale inevitably leaves evidence. For the first time, researchers possessed a strategy that did not depend on communication. They could search for consequences instead, not messages, not greetings, not radio transmissions. Engineering footprints. Imagine walking through a forest. You never see another person. You hear no voices. Yet suddenly you encounter a road, a bridge, a building. Evidence of intelligence appears even in the absence of communication. The same logic could apply on cosmic scales. A civilization might remain silent. Its constructions might not. The concept transformed scientific thinking. Perhaps the galaxy was not filled with conversations. Perhaps it was filled with artifacts. And if so, astronomers needed new ways of looking. Over the following decades, researchers began examining stars for unusual characteristics, unexpected infrared emissions, anomalous brightness patterns, signatures that might indicate large-scale engineering. The search expanded beyond radio astronomy into observational astronomy. Entirely new possibilities entered the discussion. Could advanced civilizations reshape planets, modify stars, rearrange entire solar systems? At first, these ideas sounded almost fantastical. Yet they emerged naturally from the logic of long-term growth. If humanity survived for thousands of years, our descendants would likely possess capabilities that seem extraordinary today. Given millions of years, the possibilities become even larger. The important point was not whether specific megastructures existed. The important point was that advanced civilizations should become increasingly visible through their energy use. And this observation created a paradox. The more advanced a civilization becomes, the more detectable it ought to be. Large energy consumption produces large signatures. Large engineering projects produce observable consequences. Entire stars altered by technology should stand out against natural backgrounds. Yet, despite increasingly powerful telescopes, no unambiguous examples appeared. Again, the silence persisted. The galaxy continued withholding evidence. At first, researchers assumed the answer was simple. Perhaps such civilizations were rare. After all, building stellar-scale infrastructure would require immense resources. Perhaps very few societies ever reached that level. Reasonable enough. Then, exoplanet discoveries accelerated. Thousands of new worlds entered scientific catalogues. Potential habitats appeared everywhere. The opportunities for life seemed greater than ever, and still, no confirmed megastructures emerged. The contradiction deepened. Either advanced civilizations were extraordinarily uncommon, or something else was happening. Some scientists proposed that civilizations might choose sustainability over expansion. Rather than endlessly increasing energy consumption, perhaps mature societies optimize efficiency. Perhaps they consume less rather than more. Perhaps growth itself is temporary. The idea was intriguing because it challenged a deeply human assumption. Human history often associates advancement with expansion. More energy, more resources, more territory, more production. But advanced civilizations might follow entirely different trajectories. A society capable of manipulating matter at microscopic scales could accomplish enormous tasks with comparatively little energy. A civilization focused on digital environments might require fewer physical resources than expected. Progress might lead inward rather than outward, toward efficiency instead of scale. If true, detecting such societies becomes much harder. The universe may contain advanced civilizations whose technological sophistication far exceeds ours, while producing minimal observable signatures. The most advanced societies might also be the quietest. Again, the search encountered invisibility. A recurring theme continued appearing. Distance creates invisibility. Time creates invisibility. Communication creates invisibility. Efficiency creates invisibility. The universe seemed remarkably effective at concealing intelligence. Yet another possibility emerged. Perhaps researchers were making an even deeper mistake. Perhaps they assumed that civilizations remain motivated by the same goals indefinitely. Expansion, exploration, communication, survival. These objectives appear obvious to humanity, but would they remain obvious after 10,000 years? A million. 10 million. The question introduced an entirely new dimension to the mystery: psychology. Because every search strategy implicitly assumes something about alien minds. A civilization must want to communicate, want to expand, want to build, want to leave evidence. What if those assumptions are wrong? What if intelligence itself evolves beyond recognizable motivations? Suddenly the challenge became much more complicated. Researchers were not merely searching for technology. They were attempting to predict behavior across unknown species, unknown cultures, and potentially millions of years of development. The uncertainty expanded enormously, and yet one fact remains stubbornly difficult to ignore. Even if most civilizations remain invisible, even if many choose efficiency, even if some never expand, the sheer scale of the galaxy suggests that at least a few should leave detectable traces. At least a few should become visible. At least a few should stand out. But the evidence remained frustratingly absent. The universe continued offering possibilities without confirmation, opportunities without examples, expectations without discoveries. And this persistent absence forced scientists toward an even more unsettling question. Perhaps the problem was not how civilizations communicate, perhaps not how they generate energy, perhaps not even how they expand. Perhaps the problem was that we were looking from too far away. Because before humanity could understand alien civilizations, it first needed to understand the worlds they might inhabit. And once astronomers began discovering those worlds in enormous numbers, the mystery became stranger than ever. The galaxies suddenly appeared filled with planets, yet finding life on them proved far more difficult than anyone expected. For centuries, planets beyond the solar system existed only in imagination. Astronomers could calculate their possibility. Philosophers could debate their existence. Writers could fill entire libraries describing them, but nobody could point a telescope toward a distant star and say with certainty, "There is a world," not a theory, not a probability, a world. The situation changed dramatically during the final years of the 20th century. Suddenly, after generations of speculation, planets began appearing everywhere, not through direct photographs at first. Most remained invisible, lost within the glare of their parent stars. Instead, astronomers learned to detect them indirectly. A star would wobble slightly. A tiny dimming would appear as a planet crossed its face. Subtle clues revealed hidden worlds. What began as isolated discoveries quickly became a flood. Year after year, the catalogue expanded. Hundreds of planets. Thousands. Then thousands more. The universe seemed determined to reveal an unexpected truth. Planets were not rare. They were normal. This realization was one of the most important scientific discoveries in modern history, because for the first time humanity could stop asking whether other worlds existed. The answer was obvious. They existed everywhere. And once again, the silence became harder to explain. Imagine a future historian looking back at the early 21st century. They might identify the exoplanet revolution as the moment humanity truly understood its place in the cosmos. Not because aliens were discovered, they were not, but because Earth stopped appearing unique. Our planet became one example among countless others, one world orbiting one star within a galaxy containing hundreds of billions. The psychological shift was profound. For thousands of years, humanity occupied the center of its own story. Then astronomy expanded the stage. Earth became a planet. The sun became a star. The Milky Way became a galaxy. The galaxy became one among billions. Now, exoplanet science delivered another step. Earth became one world among innumerable worlds. And many of those worlds appeared surprisingly familiar. Some orbit within regions where liquid water might exist. Some possess rocky surfaces. Some resemble larger versions of Earth. Others orbit red dwarf stars that may burn steadily for trillions of years. Entire categories of planets appeared that had never been imagined before. The diversity was astonishing. The universe seemed extraordinarily creative. Every discovery widened the range of possibilities for life. Yet something curious happened. The more planets astronomers discovered, the more difficult the problem became. Finding worlds proved easier than understanding them. Imagine observing Earth from dozens of light years away. You might detect the planet. You might estimate its size, its orbit, perhaps even aspects of its atmosphere. But would you know that cities exist? Would you know that civilization exists? Would you detect art, language, history, the internet? Probably not. At least, not easily. The challenge is fundamental. Planets are tiny. Stars are enormous. The light from a star overwhelms the faint glow of its planets. Trying to observe a distant Earth-like world resembles attempting to see a firefly beside a searchlight from thousands of kilometers away. The difficulty is extraordinary. Astronomers became increasingly skilled at discovering planets. Determining whether those planets hosted life remained vastly harder. Determining whether they hosted intelligence was harder still. This distinction transformed the search. The universe no longer appeared empty. It appeared hidden. The difference matters. An empty universe contains no answers. A hidden universe contains answers that remain inaccessible. And accessibility turned out to be one of the central challenges of the entire search for extraterrestrial intelligence. Imagine a civilization living on a distant world. Its oceans teem with life. Its cities illuminate the night. Its scientists study the stars. Its history stretches across millennia. Yet from Earth, that world appears as a tiny fluctuation in starlight. A few photons reaching a telescope, a faint signal buried in noise. The civilization exists. The information exists. The problem lies in extracting it. Once again, the universe seemed designed to obscure. Not necessarily because life is rare, because observation is difficult. This realization inspired new strategies. If direct detection proved challenging, perhaps indirect evidence could help. Researchers began examining planetary atmospheres. Life alters environments. On Earth, biological activity transformed the atmosphere dramatically. Oxygen accumulated. Chemical signatures emerged. The planet became distinguishable from a purely lifeless world. Perhaps similar clues could reveal life elsewhere. The idea was elegant. A civilization might remain invisible. Its planet might not. Future telescopes could search for atmospheric compositions unlikely to arise naturally. Methane. Oxygen. Other combinations suggesting biological activity. For the first time, astronomers envisioned detecting life without seeing organisms directly. The implications were enormous. Humanity might discover living worlds long before discovering intelligent civilizations. The galaxy could reveal biology before revealing technology. Yet, even this hopeful possibility introduced another complication. Life and intelligence are not the same thing. Earth itself demonstrates this clearly. For billions of years, life existed without technology, without radio, without telescopes, without civilization. A biosphere does not automatically produce engineers. A habitable world does not automatically produce astronomers. The distinction reopened old uncertainties. Perhaps life is common, while intelligence remains rare. Perhaps intelligent life is common, while technological civilization remains rare. Perhaps technological civilization is common, while long-term survival remains rare. Every answer generated additional questions. Every discovery expanded the mystery. Then a particularly unsettling possibility emerged. Imagine that advanced civilizations become extremely efficient. Imagine that they minimize waste, reduce emissions, optimize resource usage, blend seamlessly into their environments. From an engineering perspective, such behavior makes sense. Efficiency often accompanies advancement, but efficiency also reduces visibility. A primitive civilization might inadvertently broadcast its existence. A mature civilization might leave almost no detectable trace. The more advanced it becomes, the harder it becomes to find. The search begins to resemble a paradox. Success makes civilizations quieter. Longevity makes them harder to detect. Optimization reduces observable signatures. The universe rewards invisibility. This idea carried profound implications. Humanity had spent decades searching for civilizations that behave in recognizable ways. Civilizations that communicate loudly, consume enormous amounts of energy, construct visible megastructures. Yet perhaps most advanced societies follow entirely different paths. The galaxy may contain intelligence everywhere, while revealing almost none of it, like an ocean filled with life beneath a perfectly calm surface. The image is difficult to dismiss, because nature repeatedly demonstrates similar patterns. Most of Earth's biosphere remains hidden from casual observation. Entire ecosystems exist beyond immediate perception. Complexity flourishes beneath appearances. Perhaps the galaxy functions similarly. Perhaps intelligence is present, but concealed, not intentionally, not maliciously, simply as a consequence of physics efficiency and time. And yet there remained one stubborn objection. Even if most civilizations become invisible, surely some would not. Surely among hundreds of billions of stars, at least a few societies would expand aggressively. At least a few would build detectable structures. At least a few would announce themselves. At least a few would leave unmistakable evidence. The fact that such evidence remained elusive continued troubling researchers. Again and again the same conclusion emerged. The silence was too persistent, too widespread, too consistent. Something fundamental was missing from humanity's assumptions. The question was no longer whether other worlds existed. That question had been answered. The galaxy was overflowing with worlds. The question was whether intelligent civilizations could remain hidden indefinitely, whether entire societies could exist beyond our ability to observe them, whether the universe naturally conceals intelligence. And as scientists explored that possibility, they began considering an idea that was even more unsettling. Perhaps the civilizations we seek are not merely hidden, perhaps they are invisible by design. Not because they fear discovery, but because the most advanced forms of intelligence may operate in ways that humanity has not yet learned to recognize. The possibility sounds almost contradictory. How can a civilization be visible enough to exist, yet invisible enough to escape detection? For most of human history, intelligence announced itself through transformation. A village became a city. The city became an industrial center. A landscape changed. Forests disappeared. Roads emerged. Lights illuminated the night. Civilization altered its environment. The greater the civilization, the more obvious the alteration became. This pattern feels so familiar that we rarely question it. Progress leaves traces. Growth leaves traces. Technology leaves traces. Yet, on cosmic scales, those assumptions may be deeply misleading. Imagine an observer studying Earth from 1,000 light-years away. The observer possesses instruments vastly superior to our own. The observer can detect planets, analyze atmospheres, measure chemical compositions, perhaps even identify broad signs of biological activity. Would that observer immediately recognize humanity? The answer is less obvious than it first appears. Earth's atmosphere certainly bears signs of life. Oxygen is abundant. Chemical disequilibria exist. The planet appears biologically active, but civilization itself occupies only a thin layer on the surface. Cities cover a tiny fraction of Earth's area. Artificial lighting is visible primarily at night. Radio emissions weaken rapidly with distance. Most evidence of humanity is surprisingly subtle when viewed from interstellar scales. A civilization can transform its own world while remaining nearly invisible to the galaxy. This observation inspired a troubling idea. Perhaps humanity has misunderstood what advanced civilizations actually look like. Not technologically, observationally. The search for extraterrestrial intelligence often assumes that greater advancement produces greater visibility. But what if the opposite is true? What if advanced societies become increasingly difficult to detect? The concept emerged gradually through several independent lines of reasoning. One involved energy, another involved computation, a third involved survival. Taken together, they painted a remarkably different picture of the future. Imagine a civilization several thousand years more advanced than humanity. Its technologies are mature, its industries highly efficient, its resource management nearly optimized. Waste becomes undesirable. Excess emissions become unnecessary. Every process is refined. Every system is engineered for maximum effectiveness. From an outside perspective, such a civilization might produce fewer detectable signatures than a younger, less efficient one. The comparison is striking. A primitive society burns enormous amounts of fuel, generates noise, produces pollution, leaks energy. An advanced society may accomplish vastly more while revealing vastly less. Progress becomes concealment. The idea feels counterintuitive because human civilization currently occupies a transitional stage. We still waste tremendous amounts of energy. We still produce visible industrial footprints. We still announce our presence through countless unintended signals. Future civilizations may not. The same principle appears in computing. Early computers occupied entire rooms. Modern devices fit inside pockets. Future systems may become smaller still, more powerful, more efficient, less visible. Advancement repeatedly moves toward miniaturization rather than expansion, toward optimization rather than spectacle. If this trend continues across centuries or millennia, the most sophisticated technologies in the galaxy may also be the least observable. A civilization could become extraordinarily capable while leaving almost no detectable footprint. The implication is profound. Humanity may be searching for the wrong kind of evidence, looking for giant monuments, massive emissions, obvious engineering, when the actual signs of intelligence are subtle beyond current detection capabilities. Then another possibility emerged, one even more unsettling. Suppose a civilization reaches extraordinary levels of technological maturity. At some point, its greatest challenges may no longer involve physical expansion. The frontier shifts inward, toward information, computation, virtual environments, digital existence. The concept appears repeatedly in discussions about the far future. A civilization might eventually discover that creating artificial worlds is easier than colonizing physical ones. Instead of crossing interstellar space, it builds vast computational realities. Instead of transforming planets, it transforms information. Instead of expanding outward, it expands inward. The energy requirements may be lower, the risks smaller, the rewards greater. Whether such a future is realistic remains uncertain, but its implications for detection are significant. A civilization focused primarily on internal development may leave remarkably little evidence visible across interstellar distances. His greatest achievements occur inside systems that outsiders cannot observe. The galaxy could contain immense civilizations whose most important activities remain hidden entirely from external view. Once again, the silence acquires a possible explanation, not absence. Privacy, not extinction, redirection. Not failure, transformation. Yet another line of reasoning approached the problem from a different angle: survival. History teaches that visibility can be dangerous. Throughout human history, isolated communities often encountered risks when discovered by more powerful groups. Biology offers similar examples. Many organisms survive by avoiding attention. Concealment becomes a survival strategy. Some researchers began wondering whether similar dynamics might apply on cosmic scales. The idea became known informally as the dark forest hypothesis. The metaphor is simple. Imagine a vast forest at night. Countless hunters move through the darkness. None knows who else is present. None understands the intentions of others. Making noise becomes risky. Revealing one's location becomes dangerous. The safest strategy may be silence. The hypothesis remains speculative. No evidence confirms it. Yet its logic is difficult to dismiss entirely. The challenge arises from uncertainty. A civilization encountering another civilization cannot immediately know its intentions. Friendship is possible. Cooperation is possible. Conflict is also possible. Across interstellar distances, communication delays make trust extraordinarily difficult to establish. Misunderstandings become inevitable. Signals require years, centuries, or millennia to travel. Decision-making becomes complicated by time itself. The result is a situation unlike anything humanity has previously experienced. No shared institutions, no common history, no rapid communication, only uncertainty. Again, the silence gains another possible interpretation, not loneliness. Caution. The remarkable thing is that none of these explanations requires civilizations to be rare. Efficient civilizations remain hidden. Digital civilizations remain hidden. Cautious civilizations remain hidden. Distant civilizations remain hidden. Short-lived civilizations remain hidden. The universe accumulates mechanisms that reduce visibility, one after another, like layers of fog obscuring a landscape. The deeper scientists explored the mystery, the more these layers seemed to multiply. And yet, a fundamental problem remained unresolved. All of these ideas focus on civilizations. But what if the obstacle appears earlier? Much earlier. Before communication, before technology, before cities, before intelligence itself. What if something in the development of life repeatedly prevents civilizations from emerging in the first place? The possibility was difficult to ignore, because despite the abundance of planets, humanity still possessed only one confirmed example of life: Earth. One world, one biosphere, one data point. And from a scientific perspective, a sample size of one is a dangerous thing. It encourages assumptions. It creates illusions of certainty. Most importantly, it hides patterns. Perhaps life is common. Perhaps intelligence is common. Or perhaps Earth represents an extraordinary exception, a rare sequence of events that seldom occurs elsewhere. If that were true, then all previous explanations might be unnecessary. The silence would not result from distance, or communication, or invisibility. It would emerge much earlier, at the very beginning of the process, long before civilizations ever have a chance to look toward the stars. And this possibility would lead researchers toward one of the most famous and unsettling ideas in modern science: the notion that somewhere between lifeless matter and a galaxy-spanning civilization lies a barrier. A barrier so difficult that very few worlds ever cross it. A barrier known as the Great Filter. The idea emerged not from astronomy alone, nor from biology, nor from physics. It emerged from a simple observation. The universe appears to provide countless opportunities for life, and yet the evidence for advanced civilizations remains absent. Somewhere between those two facts, something does not add up. The Great Filter was proposed as a way of identifying the missing step, or perhaps the missing steps. Imagine the history of civilization not as a continuous process, but as a sequence of gates. Each gate must be passed successfully before the next becomes possible. A lifeless planet must first produce life. Life must become complex. Complex life must produce intelligence. Intelligence must develop technology. Technology must survive long enough to expand. Expansion must continue across interstellar distances. Failure at any stage ends the journey. The image is useful because it transforms a vague mystery into a series of specific questions. Where is the bottleneck? Which gate is hardest to cross? Which stage eliminates most potential civilizations? The answer matters enormously because it determines whether humanity is rare or merely early. Imagine climbing a mountain range hidden inside thick clouds. You know a summit exists somewhere ahead. You know many travelers have attempted the journey, but you cannot see the path. The only evidence available is your current position. Have most travelers already fallen behind you, or are the most dangerous cliffs still waiting ahead? The Great Filter asks a similar question, and its implications are unsettling regardless of the answer. Suppose the filter lies behind us. Suppose the difficult step was the origin of life itself. Perhaps biology emerges only under extraordinarily rare conditions. Perhaps billions of habitable planets remain sterile forever. If so, Earth would be remarkable. Humanity would be remarkable. The silence would make sense because very few worlds ever begin the journey. At first glance, this sounds comforting. The danger has already been passed. The obstacle was ancient. Civilization survived it, but the evidence is ambiguous. Life appeared on Earth surprisingly early, almost as soon as conditions permitted. Some scientists interpret this as a sign that biology may emerge relatively easily. If true, the filter may not reside at the beginning. Perhaps it appears later. Then consider another possibility. Maybe simple life is common. Perhaps microbial ecosystems flourish across countless worlds. Yet complex organisms remain rare. For billions of years, Earth hosted only simple life forms. The transition toward complexity required immense spans of time. Perhaps many biospheres never make that leap. The galaxy could be filled with living planets that never produce animals, intelligence, or technology. Again, the silence becomes understandable. Life exists. Civilization does not. Yet, the uncertainty remains. Earth demonstrates that complexity can emerge, at least once. The process may be rare, or it may simply require patience. No one knows. The possibilities continue. Maybe intelligence itself is uncommon. After all, countless species have lived on Earth. Only one developed advanced technology. Intelligence sufficient for civilization may represent a narrow evolutionary pathway, rather than an inevitable outcome. A planet could remain biologically rich while never producing astronomers. Again, the mystery shifts. The silence becomes biological rather than technological. But perhaps the filter appears even later. Suppose intelligent species commonly emerge. Suppose they develop science. Suppose they build civilizations. What then? History offers sobering lessons. Complex societies are fragile. They depend upon cooperation, knowledge preservation, resource management, institutional stability. Failures can cascade. Environmental changes can destabilize entire regions. Technological capabilities create new risks. Power expands faster than wisdom. The more advanced a civilization becomes, the greater the consequences of its mistakes. This possibility is particularly troubling because it places the filter ahead of us, not behind, ahead. Humanity may have reached intelligence, reached technology, reached industrial civilization, yet still face obstacles that eliminate most technological societies. The silence would then represent a warning rather than a mystery, a cosmic graveyard hidden from view. Not because civilizations never emerged, because they failed to endure. Imagine looking across an ocean at night. No lights appear on the horizon. The darkness seems empty. Only later do you learn that countless ships attempted the crossing. Most never arrived. The absence of lights suddenly carries a different meaning. Not absence of effort, absence of success. The great filter acquires its emotional power from precisely this uncertainty. We do not know where the barrier lies. Every possibility carries profound implications. If the filter lies behind us, humanity may be extraordinarily fortunate. If it lies ahead, humanity may face challenges more difficult than any previously encountered, and there is no easy way to determine which interpretation is correct. The universe offers few clues, yet researchers continued searching. They examined biology, planetary science, evolution, civilization dynamics. Every field contributed pieces of the puzzle. None produced a definitive answer. Then another realization emerged. Perhaps the great filter is not a single event at all. Perhaps it is a collection of barriers, a sequence of increasingly difficult tests. Life must survive one challenge after another. Civilization must navigate one danger after another. Success becomes progressively less likely. The process resembles an obstacle course extending across billions of years. Most worlds fail somewhere along the route. Only a tiny fraction continue. This interpretation aligned remarkably well with what scientists were already observing. Distance creates barriers. Energy creates barriers. Time creates barriers. Communication creates barriers. Survival creates barriers. Complexity creates barriers. The universe does not appear to impose one overwhelming obstacle. It imposes many, each manageable individually, formidable collectively. And perhaps this is the deeper lesson hidden within the silence. Civilization is not a destination. It is a process, a fragile process, a temporary achievement requiring constant maintenance. The search for extraterrestrial intelligence, therefore, becomes inseparable from the study of civilization itself. To understand others, humanity must understand its own vulnerabilities, its own limitations, its own future. This shift transformed the discussion. Researchers increasingly realized that the question, "Where is everybody?" might be impossible to answer without understanding what happens to civilizations over long timescales. Not decades, not centuries, millions of years. And once the conversation expanded into those timescales, a remarkable pattern appeared. Again and again, a handful of thinkers kept returning to the same mystery. Some of the most influential scientific minds of the 20th century became fascinated by it, not because they believed aliens had already been found, but because the silence itself demanded explanation. One of them would ask a question so simple that it became legendary. Another would attempt to calculate the number of civilizations in the galaxy. A third would transform the entire discussion into a story about humanity's future. Together, they would give the mystery its most enduring form. And their ideas would shape every serious attempt to understand why the universe appears so quiet. The story of the silence was about to become personal, because before humanity could solve the mystery, it first had to understand the people who spent their lives trying to explain it. The question that launched one of the greatest scientific mysteries in modern history was asked casually, not during a major conference, not in a government report, not in a carefully prepared lecture. It emerged during lunch. The year was 1950. The location was the Los Alamos National Laboratory. The man asking the question was Enrico Fermi. Fermi was already one of the most respected scientists in the world. He had contributed to the development of nuclear physics, helped construct the first nuclear reactor, worked on some of the most significant scientific projects of the 20th century. Colleagues admired him not merely for his knowledge, but for his unusual ability to identify the essential core of a problem. Complex questions often became simple when viewed through Fermi's perspective. And on that particular day, he posed a question that seemed simple enough. Where is everybody? The context remains partly obscured by time. Accounts differ in details. Yet the essence is clear. A conversation about extraterrestrial life eventually led Fermi toward a striking observation. If the galaxy is old, if stars are abundant, if planets are common, if technological civilizations can arise, then why is there no evidence of them? The question appeared almost obvious once stated aloud, yet it carried extraordinary implications, because Fermi was not arguing that alien life was impossible. Quite the opposite. He was highlighting a contradiction. The numbers suggested that intelligent civilizations should exist. The observations suggested otherwise. Something was missing. That contradiction became known as the Fermi Paradox. Technically, it is not a paradox in the strict logical sense. It is a tension, a disagreement between expectation and observation, but the name endured because it captured the mystery perfectly. The universe appears fertile, the evidence appears absent. How can both be true? What made Fermi's observation so powerful was its simplicity. The galaxy is ancient, approximately 13 billion years old in some regions. The Sun formed relatively late. Earth formed later still. Many stars are vastly older than ours. If even a few civilizations emerged millions of years before humanity, they would possess enormous temporal advantages. Imagine a civilization only 1 million years older than ours. 1 million years sounds large from a human perspective. On cosmic scales, it is almost negligible. Yet the difference between modern humanity and our distant ancestors is measured in only tens of thousands of years. 1 million years of additional development is difficult even to conceptualize. Now imagine 10 million years, or 100 million. The timescales become staggering. Fermi understood this. He realized that the age of the galaxy creates opportunities for civilizations to spread. Even relatively slow expansion eventually covers enormous distances. Suppose a civilization establishes colonies among nearby stars. Not rapidly, not through science fiction miracles, simply through gradual expansion, a few light years at a time. Over thousands or millions of years, such growth accumulates. The process resembles the spread of life itself. Small advances repeated across immense periods. The mathematics become difficult to ignore. A civilization expanding slowly enough to appear almost stationary on human timescales could still traverse the galaxy within a fraction of its total age. And yet no evidence appeared. No confirmed colonies. No unmistakable engineering projects. No obvious visitors. Nothing. The silence persisted. Fermi's question became famous because it compressed all these observations into 4 words. Where is everybody? The beauty of the question lies in its refusal to accept easy assumptions. It does not claim aliens exist. It does not claim aliens do not exist. It merely asks why expectation and observation diverge so dramatically. For decades afterwards, scientists returned to the question repeatedly. Some proposed that intelligent life is extraordinarily rare. Others argued that civilizations destroy themselves. Still others suggested that expansion across interstellar distances proves far harder than initial calculations imply. Each explanation addressed part of the mystery. None resolved it completely. The question survived, and as astronomy advanced, it became even more difficult to dismiss, because many of Fermi's uncertainties gradually disappeared. Planetary systems were discovered, exoplanets multiplied, habitable environments appeared increasingly plausible. The opportunities for life expanded dramatically, yet the silence remained unchanged. The paradox grew stronger rather than weaker. Imagine being a detective investigating a missing person. Initially, the lack of evidence may seem understandable. Little information exists. Few clues are available. Then new evidence emerges. More witnesses, more records, more opportunities for discovery. Yet the person remains missing. The mystery deepens. The search for extraterrestrial intelligence followed a similar trajectory. Every new discovery increased the expected number of potential civilizations. The observations remained stubbornly empty. Fermi's question continued haunting the field, and perhaps more importantly, it changed how scientists thought about the problem. Before Fermi, discussions about extraterrestrial life often focused on possibility. After Fermi, discussions increasingly focused on absence. The silence itself became data, a fact requiring explanation, an observation demanding interpretation. The distinction mattered, because once silence becomes evidence, every explanation must account for it. Distance alone is insufficient. Time alone is insufficient. Energy alone is insufficient. Any successful theory must explain why the galaxy appears so quiet, despite offering so many opportunities for life. This requirement elevated the discussion from speculation to analysis. Researchers began constructing models, estimating probabilities, exploring long-term scenarios. The mystery became increasingly quantitative, and no one embraced that challenge more enthusiastically than a young astronomer who happened to be launching humanity's first serious listening experiment. His name was Frank Drake. Where Fermi asked the question, Drake attempted to count the possible answers. He wanted to know how many civilizations might exist in the galaxy right now. Not eventually, not historically. Now. The effort was audacious. How do you estimate something that has never been observed? How do you calculate the abundance of unknown civilizations? The task seemed impossible. Yet Drake believed it could be approached systematically. Not solved, approached. His method would become one of the most famous intellectual exercises in modern science, not because it provided certainty, but because it transformed a mystery into a framework, a way of thinking, a way of organizing ignorance, and perhaps most importantly, a way of revealing how much humanity still did not know. The question, where is everybody, was about to acquire numbers. Those numbers would inspire generations of scientists. They would also expose just how enormous the uncertainty really was. Because once researchers began estimating the number of civilizations in the galaxy, they discovered that the answer could range from almost none at all to millions. In 1961, a small group of scientists gathered at the Radio Observatory in Green Bank, West Virginia. The meeting was modest. No global headlines followed. No major announcement emerged. No revolutionary discovery was revealed. Yet the ideas discussed there would shape the search for extraterrestrial intelligence for generations. At the center of the gathering stood Frank Drake. Unlike Enrico Fermi, Drake was not primarily interested in framing the mystery. He wanted a method for exploring it. The problem was obvious. How can scientists discuss the number of extraterrestrial civilizations when no extraterrestrial civilizations have been observed? The question seemed impossible. Most fields of science begin with data. The search for intelligent life appeared to begin with almost none. Yet Drake recognized something important. Even when precise answers are unavailable, useful questions can still be asked. A complex problem can often be broken into smaller pieces. Some pieces may be measurable, some may remain uncertain. But the structure itself can clarify thinking. To guide discussion, Drake wrote a simple equation on a board. Today, it is known as the Drake equation. It remains one of the most famous equations in modern science, not because it produces a definitive answer, but because it organizes one of humanity's greatest uncertainties. The equation asks a deceptively simple question. How many detectable civilizations exist in our galaxy right now? To answer it, Drake divided the problem into stages. How often do stars form? How many possess planets? How many planets might support life? How often does life emerge? How often does intelligence arise? How often does technology develop? How long do technological civilizations remain detectable? Each term represents a gateway, a transition, a step in the long journey from cosmic dust to radio telescopes. The brilliance of the equation lies not in solving the mystery. Its brilliance lies in revealing where the mystery actually resides. Some terms can be estimated reasonably well, others remain almost completely unknown, and as astronomy advanced, this distinction became increasingly important. When Drake first proposed the equation, scientists knew almost nothing about planets around other stars. Today, the situation is dramatically different. Modern astronomy suggests that planets are abundant, perhaps extraordinarily abundant. One of the largest uncertainties in the equation has shrunk considerably. The universe appears highly efficient at producing worlds. Likewise, stars themselves are not rare. The Milky Way contains hundreds of billions. Star formation appears to be a common process throughout cosmic history. Again, uncertainty decreased. The early stages of the equation became increasingly well understood. Yet, as researchers moved further along the chain, confidence declined rapidly. Life remains mysterious. Intelligence remains mysterious. Civilization remains mysterious. Longevity remains mysterious. The farther one travels from astronomy toward biology and culture, the less certainty exists. Imagine constructing a bridge across a canyon. The first sections are solid, well supported, carefully measured. Then the structure extends outward into fog. The foundations remain reliable. The destination becomes increasingly uncertain. The Drake equation functions similarly. It begins with stars and planets which astronomers can observe. It ends with civilizations which humanity has never observed beyond Earth. The uncertainty grows with every step. And yet the equation transformed scientific thinking because it made one fact impossible to ignore. The answer depends enormously on how long civilizations survive. Consider two scenarios. In the first, technological societies typically remain detectable for only a few hundred years. Perhaps they transition to quieter technologies. Perhaps they collapse. Perhaps they disappear. The details do not matter. The result is the same. At any given moment, relatively few civilizations are visible. The galaxy appears quiet. Now imagine a second scenario. Civilizations survive for millions of years. Their detectable phases persist. Their technological footprints endure. Suddenly the galaxy becomes crowded. Not necessarily physically crowded, observationally crowded. The difference is dramatic. A civilization lasting 1,000 times longer becomes 1,000 times more likely to be detected. Longevity amplifies visibility, and this observation connected directly to the mystery of the silence. Perhaps the key variable was not how often civilizations emerge, perhaps it was how long they endure. A galaxy filled with short-lived civilizations can appear empty. A galaxy containing only a few long-lived civilizations can appear active. Time changes everything. The insight carried profound implications because it shifted attention away from origins and toward futures. The crucial question became not merely how intelligence begins, but how intelligence persists. Humanity had spent centuries asking where civilization comes from. Now, scientists increasingly asked how civilization survives. The distinction matters because survival is not automatic. Earth's history provides ample evidence. Empires rise and fall. Institutions emerge and disappear. Languages evolve. Knowledge is lost. Knowledge is rediscovered. Stability requires effort. Continuity requires maintenance. The larger the system, the greater the challenge. And technological civilization introduces entirely new risks. Power grows. Capabilities expand. Consequences increase. The future becomes difficult to predict. The Drake equation therefore became something unexpected, not merely a tool for estimating alien civilizations. A mirror, a framework for thinking about humanity itself. Every uncertainty about extraterrestrial life reflected an uncertainty about our own future. Will technological societies endure? Will they expand? Will they remain detectable? No one knew, because humanity had not yet lived long enough to answer. The equation transformed the search for extraterrestrial intelligence into a study of civilization across cosmic timescales. And the more researchers explored those timescales, the more they encountered another influential figure, a scientist who combined astronomy, biology, history, philosophy, and storytelling in a way few others could. A scientist who believed that the search for extraterrestrial intelligence was ultimately a search for perspective. His name was Carl Sagan. Sagan approached the mystery differently from both Fermi and Drake. Fermi emphasized the contradiction. Drake emphasized the numbers. Sagan emphasized the journey. He understood something profound. The search for extraterrestrial intelligence was never only about aliens. It was also about humanity's future. Every question about another civilization eventually becomes a question about our own. How long can knowledge survive? How long can cultures endure? How long can intelligence persist in a universe governed by entropy, distance, and time? The deeper Sagan explored those questions, the more the mystery expanded beyond astronomy. The silence no longer appeared to be merely a scientific puzzle. It became a civilizational puzzle, a story about survival across immense spans of time. And once that perspective emerged, the search changed again. Because perhaps the most important question was not where civilizations are. Perhaps the most important question was whether any civilization can remain visible long enough to matter on galactic scales. By the time Carl Sagan entered the conversation, the mystery had already acquired numbers, probabilities, and equations. Scientists could estimate stars, estimate planets, estimate possibilities, yet something remained missing: the human dimension. Because a civilization is not merely a collection of technologies. It is a story, a fragile continuity of memory stretching across generations. A civilization survives only if knowledge survives, and knowledge survives only if enough people choose to preserve it. Sagan understood this deeply. Born in 1934 in Brooklyn, he grew up during an era when astronomy was transforming rapidly. Humanity moved from speculation about the planets to direct exploration, from wondering whether other worlds existed to sending machines toward them, from imagining the cosmos to beginning to measure it. Yet Sagan's most important contribution was not a single discovery. It was a way of thinking. He consistently asked humanity to look at itself from a larger perspective, not from the viewpoint of a city or a nation, or even a planet, but from the perspective of cosmic time. And when viewed through that lens, the search for extraterrestrial intelligence became something very different. Imagine a civilization lasting 100 years. By human standards, that seems substantial. Entire generations live and die. History unfolds. Technologies emerge. Cultures evolve. Now imagine a civilization lasting 1,000 years. Then 10,000. Then 1 million. Each increase changes the scale of the problem. The challenge is no longer invention. It becomes continuity. Can institutions survive? Can values survive? Can knowledge survive? Can meaning survive? These questions fascinated Sagan because they connected directly to the silence. Suppose intelligent life emerges frequently. Suppose technological civilizations appear across the galaxy. What determines whether any of them remain detectable? Longevity. Again and again, the same answer appeared. Longevity transforms probability. A civilization surviving for 1 million years becomes vastly more important to the galactic landscape than a civilization surviving for a century. Not because it is more intelligent, because it has more time. Time amplifies everything. Time allows exploration, expansion, adaptation, learning, recovery from mistakes. Most importantly, time allows civilizations to overlap with one another. A galaxy filled with short-lived societies may appear empty. A galaxy containing even a handful of extremely durable societies may appear connected. The distinction is profound. Sagan recognized that the search for extraterrestrial intelligence was fundamentally a search for survivors, not merely intelligent beings, survivors. Imagine wandering through the ruins of ancient cities on Earth. The stones remain. The builders are gone. History survives only because fragments endured. Now extend that idea across millions of years and thousands of stars. The challenge becomes extraordinary. What traces can survive? What evidence persists? What stories remain visible? The question is no longer technological. It becomes archaeological, cosmic archaeology. Every signal, every artifact, every possible clue becomes part of a search for civilizations that successfully navigated immense spans of time. This perspective led Sagan toward another realization. Humanity tends to think of intelligence as an achievement. Evolution produces intelligence. Civilization follows. Problem solved. The universe, however, may not work that way. Intelligence may be only the beginning. A species capable of building technology also acquires the power to alter its environment dramatically, to reshape ecosystems, to modify planetary systems, to influence its own future. With greater power comes greater responsibility, not as a moral principle, as a practical reality. Mistakes become more consequential. Technological capability increases faster than biological adaptation. Civilizations must learn to manage powers that evolution never prepared them to possess. The challenge becomes one of wisdom rather than intelligence. And wisdom is difficult to measure. A society may solve engineering problems while failing social ones. It may master energy while struggling with governance. It may build extraordinary machines while neglecting long-term stability. The history of Earth already provides countless examples. Short-term incentives often conflict with long-term survival. Individuals think differently from institutions. Institutions think differently from civilizations. Aligning these timescales is remarkably difficult. Sagan frequently emphasized that the future depends upon overcoming precisely such challenges. The search for extraterrestrial intelligence therefore becomes inseparable from questions about civilization itself. What qualities allow societies to endure? What behaviors promote longevity? What mistakes prove fatal? No telescope can answer these questions directly, yet they may determine whether civilizations remain visible at all. This insight shifted the mystery again. The silence no longer appeared solely as an astronomical puzzle. It became a test of civilizational resilience. Perhaps many worlds produce intelligence. Perhaps many produce technology. The harder challenge may be preserving both, across centuries, across millennia, across geological timescales. And once researchers began thinking in those terms, a disturbing possibility emerged. What if the universe is filled with civilizations that almost succeeded? Societies that reached technological maturity. Societies that explored their solar systems. Societies that dreamed of the stars, yet ultimately failed to cross some critical threshold. The image is haunting. Not a galaxy devoid of intelligence. A galaxy filled with unfinished stories. Worlds that came close. Civilizations that flourished briefly. Moments of brilliance extinguished before they could spread. If true, the silence becomes understandable. The universe does not lack beginnings. It lacks continuations. The idea resonated because it connected naturally with another emerging concept, one that would become increasingly influential during the late 20th century. The Great Filter. Researchers realized that Sagan's emphasis on survival aligned perfectly with the filter hypothesis. The critical obstacle might not lie in the emergence of life, nor intelligence, nor technology. The critical obstacle might be persistence, the ability to remain stable, adaptable, and resilient over immense periods of time. If most civilizations fail that test, the silence becomes almost inevitable. The galaxy may repeatedly generate intelligence, while rarely producing permanence. This realization carried an uncomfortable implication for humanity. The search for extraterrestrial intelligence was no longer just about finding others. It was about understanding our own prospects. Every theory about alien civilizations contained a hidden prediction about human civilization. If long-term survival is rare, humanity faces a difficult future. If long-term survival is common, then perhaps the silence demands a different explanation. Either way, the mystery points back toward us, and that is why Sagan viewed the search as profoundly important, even if no alien signal ever arrived. The effort forces civilization to think on longer timescales, to consider futures extending beyond elections, generations, and even nations, to imagine humanity as part of a story measured in millions of years. Few scientific questions demand such perspective, yet one problem remained. The Great Filter explained the silence only if a major obstacle existed somewhere along the path. A bottleneck. A barrier. a threshold difficult to cross. But what exactly was it? Where did it occur? Behind us, ahead of us. Researchers could not agree. And as the debate intensified, the Great Filter evolved from an abstract concept into one of the most unsettling possibilities in modern science. Because depending on its location, it might reveal not only why the universe appears silent, but also what humanity's future may look like. The most unsettling aspect of the Great Filter is not that it exists, it is that we do not know where it is. Imagine walking through an immense desert at night. Far behind you stands a mountain range. Somewhere ahead lies another. You know one of them contains a deadly pass that almost nobody crosses. The problem is simple. You do not know which one. If the dangerous passage lies behind you, then survival itself is extraordinary good fortune. If it lies ahead, then the greatest challenge has not yet arrived. This uncertainty sits at the heart of the Great Filter, and it transforms the silence of the universe into something deeply personal. For decades, scientists attempted to identify potential filters. Some lie within biology, others within civilization. Still others emerge from physics, economics, ecology, or psychology. Each possibility carries a different implication. Each tells a different story about humanity's future. Consider the origin of life. Despite enormous progress in biology, researchers still do not fully understand how lifeless chemistry became living systems. Earth provides evidence that it happened, but the exact pathway remains uncertain. Perhaps the transition is common. Perhaps it is extraordinarily rare. If life itself represents the Great Filter, then humanity may already belong to a tiny minority of worlds that succeeded. The galaxy could contain countless habitable planets. Most remain sterile. The silence becomes understandable. Then there is complex life. For billions of years, Earth hosted only simple organisms. Single-celled life dominated the planet for immense stretches of time. The emergence of large, complex organisms required a series of remarkable biological innovations. Perhaps this transition represents the bottleneck. Perhaps microbial worlds are abundant while animal worlds remain scarce. Again, the silence acquires an explanation. Life exists. Civilization does not. The possibilities continue. Intelligence may be rare. Technological capability may be rare. The combination of curiosity, cooperation, abstraction language, and tool use may represent an unusual evolutionary outcome. Earth contains millions of species. Only one constructed radio telescopes. Only one developed astrophysics. Only one began searching for extraterrestrial civilizations. Maybe intelligence itself is the filter. But as researchers examined these possibilities, many found themselves drawn toward a different category. Future filters. Challenges that emerge after civilization develops advanced technology. This possibility is especially disturbing because humanity has already entered that stage. The question ceases to be historical. It becomes contemporary. Imagine a civilization mastering energy, industrializing rapidly, connecting its planet through communication networks, acquiring the ability to alter ecosystems, engineer biology, and manipulate increasingly powerful technologies. The opportunities are extraordinary. The risks expand as well. A primitive society possesses limited capacity for self-destruction. An advanced society possesses much more. The relationship between power and responsibility becomes increasingly important. Not philosophically, practically. The consequences of mistakes grow larger. Civilizations create technologies faster than they create experience using them. Every generation inherits capabilities that previous generations never confronted. The pattern is visible throughout human history. Agriculture transforms societies. Industrialization transforms societies. Nuclear technology transforms societies. Digital networks transformed societies. Artificial intelligence may transform societies. Each innovation solves problems while creating new ones. Progress generates both opportunity and complexity. This observation led some researchers toward a sobering conclusion. Perhaps many civilizations reach technological maturity. The challenge lies in surviving it. Not because catastrophe is inevitable, because complexity accumulates. The larger and more interconnected a civilization becomes, the more difficult long-term stability may become. Imagine balancing a small object on your finger. Difficult, but manageable. Now imagine balancing an entire city. The challenge scales dramatically. Civilizations operate similarly. Maintaining social cohesion, resource distribution, governance, infrastructure, and knowledge preservation across centuries is extraordinarily demanding, and yet survival on galactic timescales may require exactly that. The Great Filter, therefore, expands beyond science. It enters the realm of civilization design. What institutions endure? What cultures adapt? What systems remain resilient? The search for extraterrestrial intelligence becomes inseparable from the study of long-term survival. At this point, another remarkable realization began influencing the discussion. The silence itself may provide information, not precise information, probabilistic information. Suppose galaxy-spanning civilizations were easy to create. Suppose expansion across the stars routinely succeeded. Suppose long-term survival posed few difficulties. Under those assumptions, the galaxy should eventually become visibly transformed. The timescales are simply too large. Even slow expansion accumulates over millions of years. Yet, the evidence remains elusive. This does not prove that expansion never occurs. It suggests that some limiting factor exists. Something repeatedly slows, redirects, or prevents large-scale growth. The universe appears resistant to becoming crowded. The observation is subtle but important. Many early visions of the future assumed continual expansion. Humanity spreads outward, colonizes star systems, builds larger infrastructures, occupies increasing volumes of space. The model feels intuitive because it resembles historical patterns on Earth. But the cosmos may operate differently. The distances are greater, the timescales longer, the costs higher, the incentives less obvious. Expansion may prove much harder than intuition suggests, or perhaps mature civilizations simply pursue different goals. Again, uncertainty dominates, and uncertainty creates a peculiar psychological effect. Every explanation remains plausible. No single theory commands overwhelming evidence. The silence accommodates many interpretations simultaneously. This is why the mystery has endured for decades, not because scientists lack ideas, because too many ideas remain viable. The universe refuses to provide decisive answers. Yet, despite all this uncertainty, one conclusion became increasingly difficult to avoid. The search for extraterrestrial intelligence is not merely a search for life. It is a search for civilizations that survived, civilizations that navigated whatever filters exist, civilizations that endured long enough to become visible across cosmic distances. The distinction matters enormously. Finding microbial life elsewhere would be transformative. Finding intelligent life would be even more profound. Finding a civilization that survived for millions of years would answer an entirely different question. It would demonstrate that long-term persistence is possible, that intelligence can endure, that the silence is not absolute. And perhaps that realization explains why the search continues despite decades of uncertainty. Researchers are not only searching for neighbors, they are searching for examples. Proof that civilization can remain stable across immense stretches of time. Proof that intelligence can survive the challenges it creates. Proof that the story does not inevitably end. Because hidden beneath every discussion about extraterrestrial life lies a deeper question. A question about humanity itself. Can a technological civilization become a long-lived civilization? Can knowledge survive? Can culture survive? Can meaning survive? The answers remain unknown. But as the 20th century gave way to the 21st, a new generation of scientists began approaching the mystery differently. Instead of focusing on radio signals or probability equations, they started examining the universe itself. Space, time, information, the architecture of reality, and what they discovered suggested that the silence might not result from biology or civilization alone. The obstacle could be far more fundamental. The universe itself may naturally separate intelligent species, not through hostility, not through intention, but through the way information moves across cosmic distances. The search was about to shift from civilizations to the structure of reality itself. For most of the 20th century, the search for extraterrestrial intelligence focused on a simple assumption. If civilizations exist, they should eventually become visible through radio, through engineering, through exploration, through some detectable activity. The challenge was finding the evidence. But by the beginning of the 21st century, another possibility began attracting attention. What if visibility itself is the wrong concept? What if the deeper issue involves information? The distinction may seem subtle. It is not. Because information obeys rules, and those rules are woven directly into the structure of the universe. Imagine two people standing on opposite sides of a mountain. Both are alive. Both are capable of communication. Both are actively searching for one another. Yet neither can see the other. The obstacle is not intelligence, not motivation, not technology. The obstacle is the landscape between them. Now scale that image upward. Not a mountain. Interstellar space, not kilometers. Light years, not human lifetimes. Cosmic timescales. The challenge begins to look very different. Throughout earlier sections of our journey, the same theme has appeared repeatedly. Distance delays information. Time separates civilizations. Energy limits expansion. Signals weaken. Visibility declines. The deeper scientists explored these obstacles, the more they realized they share a common foundation. Information travels slowly, or, more precisely, information travels at a finite speed. That single fact may shape the entire history of intelligence in the universe. Consider how profoundly different reality would be if information traveled instantly. A civilization on Earth could communicate with another civilization thousands of light years away as easily as sending a message across a city. Knowledge would spread rapidly. Cultures could exchange ideas. Networks could emerge across immense distances. The galaxy might function as a connected community, but the universe does not permit this. Information moves no faster than light. Every message experiences delay. Every observation looks into the past. Every interaction becomes constrained by distance. The result is remarkable. Civilizations are not merely separated spatially, they are separated temporally. Each occupies its own informational horizon, its own bubble of awareness. Imagine Earth as a small island surrounded by an expanding sphere of information. For approximately 100 years, radio signals have been leaking into space. That sphere now extends roughly 100 light years in every direction. Within it, evidence of humanity exists. Beyond it, humanity remains effectively unknown. The same logic applies to every civilization. Each creates a growing bubble of detectable information. The galaxy becomes a collection of overlapping and non-overlapping awareness zones. Some civilizations may never intersect, not because they are absent, because their informational spheres never meet. This realization led researchers toward a profound insight. The universe naturally fragments knowledge. No observer possesses access to the whole picture. Every civilization sees only a tiny portion of reality, a limited region, constrained by distance and time. The implication is extraordinary. The apparent silence may partly result from perspective, not from absence. Civilizations may exist beyond our observational reach, not hidden intentionally, simply too distant for information to arrive. The distinction matters because it changes the nature of the mystery. The question becomes less, where are they? And more, what information can possibly reach us? Astronomers encounter this limitation constantly. When observing distant galaxies, they do not see those galaxies as they are. They see them as they were. Millions, sometimes billions of years ago. The universe continuously presents history rather than immediacy. This temporal separation affects every search for intelligence. A civilization detected today may no longer exist. A civilization existing today may remain undetectable. Information lags reality. The larger the distance, the greater the divergence. In some cases, civilizations may effectively miss one another despite occupying the same galaxy. Imagine two societies separated by 20,000 light years. Each survives for 10,000 years. Each develops advanced technology. Each searches for extraterrestrial life. Neither ever detects the other. The signals arrive too late. The histories fail to overlap. The civilizations become strangers, separated not merely by space, but by chronology. The image is haunting. A galaxy filled with intelligence. A galaxy filled with curiosity. A galaxy filled with unanswered questions. Yet communication never occurs because information cannot move quickly enough. The architecture of space-time itself creates isolation. Researchers increasingly recognize that this problem extends far beyond extraterrestrial intelligence. It affects every attempt at large-scale coordination. Suppose a civilization expands across multiple star systems. At first, the achievement seems extraordinary. Humanity dreams of such futures. Interstellar settlements, distributed populations, multiple worlds connected by shared history. Then the communication delays begin. A colony 10 light-years away receives messages a decade late. A response requires another decade. A conversation becomes a 20-year exchange. Expand farther, and the delays become longer. Governance becomes difficult. Coordination becomes difficult. Shared identity becomes difficult. Distance gradually transforms unity into separation, not through conflict, through physics. The larger the civilization, the harder coherence becomes. This observation produced a striking reversal. Many people assume that bigger civilizations naturally become stronger. On planetary scales, this is often true. On interstellar scales, the situation becomes more complicated. Growth creates fragmentation. Expansion creates informational distance. Communication slows. Synchronization weakens. The challenge is not merely building a civilization. It is keeping one connected. Again, the universe appears to reward separation. Not because separation is desirable, because separation emerges naturally from the laws governing information. This realization inspired a new generation of thinking. Perhaps intelligent life should not be imagined as a single galactic empire. Perhaps the future resembles something far more decentralized. Clusters of worlds, independent regions, local civilizations connected loosely, if at all. The galaxy may never become a unified community. It may remain a mosaic, a patchwork of isolated histories, each region evolving largely on its own. The implications for the search are profound. Humanity may be waiting for evidence of a galaxy-wide civilization when reality contains only local ones, civilizations large enough to matter within their regions, too distant to influence ours. Again, the silence acquires another possible explanation. Not extinction, not rarity, fragmentation. The universe naturally partitions information, and the more researchers studied this partitioning, the more they noticed something remarkable. The effect appears everywhere. In communication, in exploration, in governance, in culture, in observation. Again and again, reality seems structured in ways that discourage connection across immense distances, not prohibit it entirely, simply make it extraordinarily difficult. The realization was subtle, yet it represented a major shift. The search for extraterrestrial intelligence was no longer just a search for other beings. It became an investigation into the architecture of cosmic isolation itself. And once scientists began viewing the problem through that lens, they encountered an even deeper possibility. Distance may not be the ultimate barrier. Information may not be the ultimate barrier. The greatest obstacle could be time, because even if civilizations overcome distance, even if they exchange information, even if their signals intersect, they must still exist during the same narrow window of cosmic history, and the universe is far older than any civilization humanity has ever imagined. At first, time appears less threatening than distance. Distance feels tangible, a measurable separation between places. Time seems familiar. Human beings live within it constantly. We schedule our lives around it. We record history through it. We rarely think of it as an obstacle. Yet on cosmic scales, time may be the most powerful barrier of all. A civilization can attempt to overcome distance. It can build faster spacecraft, larger telescopes, more powerful transmitters. Time is different. Time cannot be bypassed so easily. It shapes every process in the universe, every star, every planet, every species, every civilization. And when researchers began examining cosmic history carefully, they discovered something remarkable. The universe is not merely large, it is staggeringly asynchronous. Events do not occur everywhere at once. Worlds do not develop together. Civilizations do not emerge simultaneously. Instead, the galaxy resembles a landscape filled with clocks, each running according to its own schedule. Some began ticking billions of years before Earth existed. Others have barely started. Imagine walking through a city at night. Every building contains a different story. Some people are waking up. Some are eating dinner. Some are sleeping. Some are working. everyone occupies the same city, yet they inhabit different moments. Now imagine scaling that idea to an entire galaxy. One planet may host microbial life, another may host intelligent beings, a third may contain the ruins of a civilization that vanished millions of years ago, a fourth may remain lifeless. All coexist within the same cosmic neighborhood, yet their histories rarely align. The universe does not synchronize development, and this observation changes everything. Throughout earlier sections, we explored distance, energy, communication, survival, and information. All are formidable challenges, but they assume that civilizations overlap in time. What if most do not? What if the galaxy resembles a vast museum rather than a crowded city? Rooms filled with exhibits from different eras, each existing separately, each isolated by chronology. The possibility becomes surprisingly plausible when considering the age of the Milky Way. Our galaxy formed more than 13 billion years ago. Earth is less than 5 billion years old. Modern technological civilization is barely 100 years old. The scales differ enormously. Humanity occupies a tiny sliver of galactic history, a brief flicker within an ancient cosmos. Imagine a civilization that emerged 100 million years ago. Not 1 billion, not 10 million, 100 million. By geological standards, the interval is modest. Dinosaurs still walked Earth 100 million years ago. Flowering plants were only beginning to spread. No humans existed. No primates. No mammals resembling us. Now imagine a civilization developing elsewhere during that period. If it survived, its age would exceed human civilization by an almost incomprehensible margin. If it vanished, its disappearance occurred long before humanity appeared. Either way, direct interaction becomes unlikely. The chronological gap is simply too large. This realization led scientists toward a profound conclusion. The search for extraterrestrial intelligence may be less like meeting neighbors and more like studying history. A civilization detected tomorrow might represent a culture long gone. Signals arriving today could have been transmitted before human civilization existed. The universe continuously mixes present observations with ancient events. The distinction between archaeology and astronomy begins to blur. Every signal becomes a fossil. Every observation becomes a historical document. The implications are unsettling. Humanity often imagines contact as a conversation, a greeting exchanged between contemporaries. Yet, cosmic reality may not permit such encounters frequently. Instead, civilizations may discover traces of one another across time. Artifacts, signals, environmental modifications, evidence rather than interaction. The universe may allow discovery while preventing dialogue. Again, the silence gains another interpretation, not because civilizations never existed, because most existed at different times. Imagine standing on a beach and watching waves arrive. Each wave reaches the shore separately. The ocean contains countless motions occurring simultaneously, yet any given observer experiences only a small subset. Civilizations may resemble those waves, emerging, expanding, declining, disappearing. Their histories overlap only occasionally. The galaxy becomes a dynamic process rather than a static population. Researchers began constructing models based on this idea. The results were illuminating. Even if intelligent civilizations emerge regularly, overlap remains surprisingly difficult. Long distances amplify delays. Short civilization lifetimes reduce coincidence. Technological windows remain brief. The combined effect dramatically lowers the probability of contact. The silence becomes less mysterious. Not inevitable, statistically understandable. Then another observation deepened the picture. Stars themselves evolve on different schedules. Some burn rapidly, others endure for trillions of years. Planetary environments change accordingly. Opportunities for life emerge at different times. The galaxy continuously generates new possibilities while extinguishing old ones. Intelligence does not appear against a fixed backdrop. It appears within a changing cosmic ecosystem. This ecosystem possesses its own chronology, its own rhythms, its own history. Humanity belongs to a specific chapter, not the beginning, not necessarily the end, merely one chapter among many. The realization is humbling. For centuries, people imagined humanity as central to the cosmic story. Modern astronomy suggests something else. There may be no central chapter, no privileged moment, no preferred observer. Every civilization experiences only a fragment of the larger narrative. The galaxy's history exceeds the perspective of any single species. Even a civilization lasting millions of years would witness only part of the story. This understanding transformed the search once again. Researchers increasingly recognize that intelligence may be isolated, not because space is empty, but because cosmic history is distributed unevenly. Civilizations inhabit different eras, different opportunities, different circumstances. The universe naturally separates them, not merely spatially, temporally. The effect resembles islands emerging and sinking within an enormous ocean. Some coexist briefly, most never meet. Yet the ocean contains all of them. This perspective offered a remarkable shift. Perhaps humanity should not expect a crowded galaxy filled with active conversations. Perhaps the more realistic expectation is occasional overlap, rare intersections between independent histories, moments when the timing happens to align, moments when signals arrive at the right place during the right century, moments when two civilizations briefly share a common horizon of awareness. If so, finding another civilization may depend on extraordinary coincidence. Not impossible, simply uncommon, and that realization pointed toward a deeper question. If contact requires such alignment, what conditions must actually be satisfied? How rare is the overlap? How many variables must cooperate simultaneously? Because researchers were beginning to suspect that discovering another civilization might require more than intelligence, more than technology, more than survival. It might require one of the rarest combinations in the universe. The right place, the right time, and the right moment in cosmic history. By this point in our journey, the silence no longer appears to arise from a single cause. It emerges from layers. Distance separates civilizations. Energy constrains expansion. Information travels slowly. Time fragments history. Survival remains uncertain. Each obstacle alone is manageable to imagine. Together they create something far more formidable, a universe that naturally resists connection. Yet one question remains unresolved. How unlikely is contact really? Not philosophically, not emotionally, mathematically. If intelligent civilizations exist throughout the galaxy, what must happen for two of them to discover one another? The answer turns out to be far more demanding than most people initially assume. Imagine two strangers attempting to meet in a city. The city is enormous. Neither knows the other's location. Neither knows the other's schedule. Neither knows how long the other will remain in the city. A successful meeting requires multiple conditions. Both must exist. Both must remain present long enough. Both must occupy roughly the same region. Both must become visible. Both must recognize the significance of what they observe. Failure at any stage prevents contact. Now replace the city with the Milky Way. Replace years with millennia. Replace neighborhoods with star systems. The challenge grows dramatically. Astronomers increasingly realize that contact is not a single event. It is the intersection of multiple probabilities. Every additional requirement reduces the odds, and the universe appears to impose many requirements. A civilization must emerge. It must develop technology. It must remain detectable. Its signals must reach another civilization. The receiving civilization must possess the ability to recognize them. Both societies must exist during overlapping periods. Both must survive long enough for information to travel between them. The list grows surprisingly long. The cumulative effect is profound. Even if intelligent life is relatively common, successful contact may remain rare, not because civilizations are absent, because coincidence is difficult. Researchers began describing this challenge as a problem of alignment, not alignment of intentions, alignment of circumstances. The right place, the right time, the right technological phase, the right observational capabilities, the right distance, the right history. The more carefully the problem is examined, the more extraordinary contact begins to appear. Imagine a civilization located 5,000 light years away. Suppose it broadcasts a detectable signal. That signal requires 5,000 years to reach Earth. Humanity must possess suitable instruments during the period of arrival. The transmitting civilization must have existed 5,000 years earlier. The signal must remain distinguishable from natural sources. Observers must recognize its significance. Many conditions must cooperate simultaneously. Any failure restores the silence. The situation becomes even more challenging when considering civilization lifetimes. Suppose technological societies typically remain detectable for only a few centuries, a surprisingly brief window. Two civilizations separated by thousands of light years may never overlap observationally. Their histories simply miss each other. One appears too early, another too late. The galaxy contains both. Neither knows the other exists. This insight transformed how scientists interpreted the absence of evidence. Silence no longer necessarily implies loneliness. It may reflect geometry and chronology working together, a kind of cosmic scheduling problem. The universe may contain many participants, yet their appearances rarely coincide. The image resembles ships crossing a vast ocean at night. Each vessel carries passengers. Each vessel possesses lights. Each vessel follows its own course. Most never encounter one another, not because the ocean is empty, because the distances are immense and the journeys brief. The analogy becomes even more striking when viewed across cosmic timescales. The Milky Way is more than 100,000 light-years across. Civilizations lasting a few thousand years occupy only tiny fractions of galactic history. The overlap opportunities become surprisingly limited. Again, the silence becomes understandable, not inevitable, statistically plausible. Then another realization emerged. Perhaps contact is not the most important outcome. Perhaps persistence is. Throughout human history, exploration has often been treated as the ultimate measure of success. Discovering new lands, crossing new frontiers, reaching new destinations. The search for extraterrestrial intelligence inherited that mindset. The goal became finding others, making contact, receiving a signal. Yet the deeper scientists examined the problem, the more another challenge appeared, remaining present long enough for contact to occur. The distinction matters. Imagine two civilizations. One expands rapidly but survives only briefly. The other grows slowly but endures for millions of years. Which is more likely to become visible? Which is more likely to encounter others? The answer is obvious. Longevity dominates. Time magnifies opportunity. A civilization surviving for 1,000,000 years experiences far more chances for discovery than one surviving for 1,000. The implication is profound. The central challenge may not be reaching the stars. It may be remaining alive long enough for the stars to matter. This realization pushed scientific thinking toward increasingly long timescales. Thousands of years, hundreds of thousands, millions. Researchers began asking questions that previous generations rarely considered. How does a civilization preserve knowledge for 1,000,000 years? How does it maintain cultural continuity? How does it adapt to changing environments? How does it survive technological transformation? How does it remain recognizable to itself? The questions extend beyond engineering. They enter psychology, sociology, philosophy. Civilization itself becomes the subject of investigation. And here the search for extraterrestrial intelligence reveals one of its most unexpected lessons. The universe may not be testing intelligence. It may be testing persistence. Many species might become intelligent. Many civilizations might become technological. Fewer may remain stable across immense stretches of time. The cosmos rewards endurance, not speed, not power, endurance. This perspective helps explain why the silence feels simultaneously discouraging and hopeful. Discouraging because contact appears difficult. Hopeful because absence of evidence does not imply absence of life. The universe may simply operate on timescales that exceed human intuition. Civilizations may be separated not by impossibility, but by patience. And patience on cosmic scales becomes extraordinary. 1,000,000 years is a long time for a species, a short time for a galaxy. The mismatch creates isolation. Again and again, the same pattern appears. The universe stretches every process. Communication, exploration, observation, history. Nothing happens quickly. Everything unfolds across vast intervals. Yet hidden within this realization lies the beginning of a breakthrough, because once researchers stopped asking how to force contact and started asking how civilizations might endure long enough for contact to become possible, the discussion changed. The focus shifted from discovery to continuity, from signals to timescales, from astronomy to civilization design. And in that shift, a remarkable possibility emerged. Perhaps the solution to the silence is not finding another civilization today. Perhaps the solution is becoming the kind of civilization that remains present tomorrow, or 1,000 years from now, or 1,000,000, because only civilizations that endure can participate in a universe where distance and time dominate everything. And once that possibility entered the conversation, the search itself began to look different. Not as a race, not as a competition, but as a long-term project extending across generations, perhaps even across entire eras of human history. The breakthrough was not technological, it was conceptual, and it would fundamentally reshape how humanity thinks about its place in a silent universe. The breakthrough did not arrive as a machine. It did not arrive as a signal. It did not arrive as a discovery hidden in a telescope image. Instead, it emerged from a change in perspective. For decades, humanity approached the silence as though it were a puzzle awaiting a clever solution. Build larger telescopes. Search more stars. Listen longer. Transmit stronger signals. Eventually, the answer would appear. Yet, as the search matured, researchers began realizing something unexpected. The universe may not be withholding answers. The universe may simply operate on timescales far larger than those of individual civilizations. And if that is true, then the search itself must evolve. Imagine a cathedral built during the Middle Ages. The workers who laid the foundations rarely saw the completed structure. Generations participated. Architects died. Builders died. Kings died. The project continued. Completion required continuity rather than immediacy. The search for extraterrestrial intelligence increasingly began to resemble such endeavors. Not a project measured in years, a project measured in centuries, perhaps millennia. This shift represented a profound conceptual breakthrough. Humanity had been thinking like individuals. The universe requires thinking like civilizations. The distinction changes everything. An individual expects answers within a lifetime. A civilization can pursue questions across generations. An individual seeks immediate results. A civilization can invest in futures it will never personally witness. The silence began to look different when viewed from this perspective. Not as a failure, as a long-term challenge. And once researchers embraced that timescale, new possibilities emerge. Suppose contact requires extraordinary coincidence. Suppose civilizations rarely overlap. Suppose signals travel for thousands of years. Suppose detectability windows remain brief. What strategy maximizes success? The answer is surprisingly simple. Remain present. Every additional century increases opportunity. Every additional millennium increases opportunity. Longevity becomes the ultimate search technology. A civilization surviving for 1,000,000 years effectively performs 1,000,000 years of observation, 1,000,000 years of listening, 1,000,000 years of learning. The probability of discovery accumulates. Patience becomes power. This realization inspired a new way of thinking about the future. Instead of focusing exclusively on contact, researchers began considering what a civilization must become in order to survive cosmic timescales. The question moved beyond astronomy, beyond engineering, beyond physics. It entered the realm of civilization architecture. How do societies endure? How do they maintain knowledge? How do they preserve adaptability? How do they remain resilient while changing continuously? Imagine Earth 10,000 years from now. Languages have evolved. Institutions have changed, technologies have transformed repeatedly, yet some continuity remains. A thread connecting distant generations. Now extend the thought experiment further. 100,000 years. 1,000,000 years. The challenge becomes almost unimaginable. Human civilization has existed for only a tiny fraction of those intervals. No historical example provides guidance. Humanity must invent entirely new approaches to continuity. Knowledge preservation becomes essential. Cultural memory becomes essential. Long-term governance becomes essential. Even identity becomes complicated. Would a 1,000,000-year civilization still consider itself the same civilization? The question sounds philosophical, it may actually be practical, because continuity requires some form of shared narrative, some reason to maintain connection across immense spans of time. The deeper researchers explored these issues, the more they recognized that survival itself is a technological achievement, not merely biological survival. Civilizational survival, the ability to absorb change without collapsing, the ability to adapt without losing coherence, the ability to preserve purpose across eras. This understanding transformed the search for extraterrestrial intelligence into something larger. The goal was no longer simply finding others. The goal became understanding the conditions under which intelligence can endure, because only enduring intelligence can overcome the barriers imposed by the universe. Distance yields to time. Information accumulates. Opportunities multiply. Persistence slowly defeats isolation. The realization carries profound implications. A civilization need not cross the galaxy immediately. It need only survive. The galaxy itself provides time. Enormous amounts of time. 1,000,000 years. 10 million. 100 million. The opportunities become vast. From this perspective, the silence acquires a different meaning. Not evidence that contact is impossible. Evidence that contact belongs to civilizations willing to think on cosmic timescales. And perhaps this is why the universe appears so quiet. Not because intelligence is absent, because patience is rare. Imagine two civilizations separated by thousands of light years. Neither can bridge the gap quickly. Neither can bypass the speed of light. Neither can force communication. Yet both survive, century after century, millennium after millennium. Eventually, their informational horizons intersect. Signals arrive. Evidence accumulates. Awareness emerges. The process is slow, yet entirely possible. Time, once viewed as the obstacle, becomes the solution. The universe does not reward urgency, it rewards endurance. This idea represents one of the most important conceptual breakthroughs in the entire mystery. The search is not fundamentally about technology. Technology helps. The search is fundamentally about timescale. A civilization that persists long enough eventually gains access to opportunities unavailable to shorter-lived societies. The future itself becomes a resource as valuable as energy, as valuable as information, as valuable as knowledge. Researchers increasingly recognize that this insight applies not only to extraterrestrial civilizations, but also to humanity. The question is no longer merely whether others exist. The question is whether humanity can become a civilization capable of participating in cosmic history, not briefly, sustainably. The distinction is crucial. A civilization lasting a few centuries contributes little to galactic processes. A civilization lasting millions of years becomes part of the structure of galactic history itself. The search, therefore, points toward a larger conclusion. The universe may not be built to prevent contact entirely. It may be built to ensure that only the most enduring civilizations achieve it. Not through intention, not through design, through the interaction of distance, time, information, and survival. Together, these forces create an extraordinary filter, one that selects for persistence. And once that realization emerged, attention naturally shifted toward the future. What would a civilization optimized for cosmic timescales actually look like? How would it organize itself? How would it educate its citizens? How would it govern itself across generations? How would it preserve meaning? Because surviving for 1,000,000 years is not merely an engineering problem. It is a human problem. And answering it may determine whether humanity remains a brief episode in cosmic history or becomes one of its long-term participants. Imagine waking up tomorrow to learn that no alien signal has been detected, no spacecraft has appeared, no ancient artifact has been discovered, nothing about the universe has changed. The stars remain silent. The galaxy remains distant. The mystery remains unresolved. Would that mean the search has failed? For much of the 20th century, many people might have answered yes. The objective seemed obvious. Find evidence. Receive a message. Confirm that humanity is not alone. Anything less felt incomplete. Yet after decades of investigation, a different perspective began to emerge. The greatest consequence of the search may not be what humanity discovers. It may be what humanity becomes. Because every serious attempt to understand the silence eventually encounters the same challenge: long-term survival. Again and again, the mystery points back towards civilization itself. The universe asks a difficult question. Can intelligence endure? Not for decades, not for centuries, for cosmic timescales. The challenge transforms everything. Most human institutions are designed around short horizons. Governments often think in years. Businesses often think in quarters. Individuals often think in lifetimes. The universe operates differently. The barriers separating civilizations are measured in millennia and light years. Participation in cosmic history requires a civilization capable of extending its perspective dramatically. Imagine a society that genuinely plans for 10,000 years. Its priorities would differ from ours. Infrastructure would be designed differently. Education would be designed differently. Environmental management would be designed differently. Knowledge preservation would become a central concern. The future would cease to be an abstraction. It would become a practical domain of responsibility. Now extend the horizon further. 100,000 years. 1 million years. The implications become profound. A civilization optimized for cosmic timescales would need remarkable resilience. Not stability in the sense of remaining unchanged. Nothing survives by remaining unchanged. Resilience means maintaining continuity while adapting repeatedly. Languages may evolve. Technologies may transform. Cultures may shift, yet some underlying framework persists. The civilization remains connected to its own history. This challenge becomes especially important when considering knowledge. Human history contains countless examples of information being lost. Libraries burned. Records disappeared. Languages vanished. Techniques were forgotten. Entire traditions collapsed. Civilizations recovered, but not always completely. On timescales of centuries, such losses are significant. On timescales of millions of years, they become existential. A civilization that repeatedly forgets may never accumulate enough continuity to participate meaningfully in cosmic history. Knowledge preservation, therefore, becomes more than an academic concern. It becomes a survival technology. Future societies may build archives designed to endure geological timescales, distributed repositories spread across planets, redundant systems preserving scientific, cultural, and historical memory. Not because nostalgia demands it, because continuity requires it. The same logic applies to governance. A civilization lasting thousands or millions of years cannot rely entirely on institutions designed for short-term conditions. It must create mechanisms capable of adaptation. Mechanisms capable of learning. Mechanisms capable of surviving changing environments without losing coherence. This is extraordinarily difficult. History demonstrates that institutions evolve, sometimes successfully, sometimes catastrophically. The challenge lies in balancing flexibility with continuity. Too rigid and a civilization becomes brittle. Too fluid and it loses identity. The universe offers no simple solutions, only consequences. Researchers increasingly realize that the search for extraterrestrial intelligence naturally leads toward these questions, because any civilization visible across cosmic distances must have solved them, at least partially. The very existence of a long-lived civilization implies success in areas humanity still struggles to understand. Not perfection, persistence. And persistence may be the rarest achievement of all. Consider the history of life on Earth. Species emerge. Species disappear. Ecosystems transform. Environments change. Extinction is common. Longevity is exceptional. The same pattern may apply to civilizations. Many beginnings, few continuations. The silence could reflect this imbalance. Not because intelligence is uncommon, because enduring intelligence is. This possibility reshapes humanity's role within the story. Instead of waiting passively for contact, civilization acquires a new objective. Become discoverable, not tomorrow, eventually. Become the kind of society capable of remaining present long enough to matter. The distinction is subtle but powerful. The search ceases to be entirely outward-facing. It becomes inward-facing as well. Every effort to improve resilience, every effort to preserve knowledge, every effort to reduce existential risk, every effort to maintain long-term stability. These actions contribute indirectly to the same goal, remaining part of the cosmic conversation, even if that conversation unfolds across millennia. Imagine humanity 100,000 years from now. The details are impossible to predict, the technologies unimaginable, the cultures transformed. Yet perhaps some continuity remains, a memory that ancient ancestors once wondered whether they were alone, a memory that they listened to the stars, a memory that they chose persistence over resignation. The image carries a certain elegance. The search succeeds not because a signal arrives immediately. The search succeeds because it motivates civilization to think beyond itself, beyond individual lives, beyond generations, beyond nations, toward planetary and eventually cosmic timescales. In that sense, the silence may already be teaching something valuable. It forces humility. It forces patience. It forces perspective. The universe refuses to accommodate short-term expectations. It invites longer horizons instead. And perhaps that invitation is more important than any particular answer, because even if another civilization is discovered tomorrow, humanity will still face the same fundamental challenge: survival, continuity, meaning. Contact does not eliminate those responsibilities, it merely reframes them. The future of civilization, therefore, depends not only on what exists elsewhere. It depends on what humanity chooses to become. A species focused exclusively on immediate concerns may remain trapped by short timescales. A civilization capable of thinking across millennia gains access to entirely different possibilities. The silence encourages the latter, and that realization leads naturally to the final question, the deepest question of all. What if the universe is not merely testing our technology? What if it is testing our perspective? What if the apparent emptiness of the cosmos is forcing intelligent beings everywhere to confront the same challenge? To decide whether they can become custodians of the future rather than merely inhabitants of the present, because ultimately the search for extraterrestrial intelligence is not only a scientific journey, it is a philosophical one, and at its end lies a question far larger than alien life. What does it mean for intelligence to endure in a universe this vast? For thousands of years, humanity has looked upward and imagined company. Ancient storytellers filled the heavens with gods. Philosophers imagined inhabited worlds. Scientists searched for signals. Engineers designed interstellar futures. Generation after generation confronted the same mystery. The stars seemed too numerous. The universe seemed too vast. Surely, somewhere, someone else must exist. And perhaps they do. By the end of our journey, that possibility remains very much alive. The silence has not disproven it. The silence has simply become more complicated than it first appeared. What began as a question about aliens gradually transformed into something much larger. A question about distance, then time, then energy, then information, then survival, then civilization itself. Each layer revealed a deeper obstacle. Each obstacle revealed a deeper perspective, and together they suggested a remarkable possibility. The universe may not be empty. The universe may be difficult. Difficult in ways that human intuition rarely anticipates. When people imagine contact between civilizations, they often picture a dramatic moment. A signal decoded, a spacecraft arriving, a message received, a discovery changing history overnight. Reality may unfold differently. The universe appears structured around patience. Stars evolve slowly. Galaxies evolve slowly. Life evolves slowly. Civilizations may need to think slowly as well. Not in the sense of inactivity, in the sense of long-term perspective. The cosmos rewards duration. Again and again that lesson appeared throughout our investigation. Distance favors endurance. Communication favors endurance. Discovery favors endurance. Survival favors endurance. The future itself becomes the most valuable resource a civilization can possess. This realization changes the meaning of the silence. At the beginning of our story, the silence seemed discouraging. An absence, a failure, a mystery demanding explanation. Now it appears differently. The silence is information. Not complete information, not satisfying information, but information nonetheless. It tells us that intelligence does not spread effortlessly across the galaxy. It tells us that communication is difficult. It tells us that survival matters. It tells us that cosmic history operates on scales far beyond ordinary human experience. Most importantly, it reminds us that the universe is under no obligation to be convenient. Reality is not arranged around our expectations. The cosmos follows its own rules, and those rules appear to create isolation naturally. Not necessarily permanent isolation, but profound isolation. Imagine a vast ocean stretching beyond every horizon. Scattered across that ocean are islands. Each island supports life. Each develops its own culture, its own history, its own stories. The inhabitants gaze across the water and wonder whether other islands exist. Some eventually discover evidence, a distant light, a drifting artifact, a signal carried by the waves. Most spend long periods alone, not because the ocean is empty, because the ocean is immense. The galaxy may resemble such a place, not a crowded city. An archipelago of civilizations, separated by extraordinary distances, separated by extraordinary timescales, occasionally connected, usually isolated. The image is humbling, yet it is not hopeless, because isolation and loneliness are not the same thing. A civilization can be isolated without being insignificant. A civilization can be isolated while still participating in a larger story. Humanity already participates in such a story. Every observation of a distant galaxy connects us to events millions or billions of years old. Every telescope extends awareness beyond our immediate surroundings. Every scientific discovery expands the horizon of understanding. Even before contact occurs, knowledge creates connection. This may be one of the most important lessons hidden within the search. The value lies not only in finding others, the value lies in learning how to think on larger scales, larger than individual lives, larger than nations, larger than centuries. The search encourages civilization-sized thinking, and civilization-sized thinking naturally leads toward responsibility. If humanity is rare, responsibility increases. If humanity is common, responsibility still increases. Either way, intelligence becomes precious, because intelligence is the mechanism through which the universe becomes aware of itself. The phrase is often repeated, yet its implications remain extraordinary. For billions of years, Earth existed without observers capable of understanding stars. Then intelligence emerged. A tiny region of matter began asking questions about the cosmos, began studying galaxies, began investigating the origins of life, began wondering whether other minds existed elsewhere. The universe gained the ability to contemplate itself. Perhaps that process has occurred many times, perhaps only rarely. We do not yet know, but we do know that it happened here, and that fact alone carries significance. Throughout our journey, we repeatedly encountered barriers: distance, energy, time, information. The great filter, civilizational fragility. Each seemed capable of preventing contact, yet none completely eliminated possibility. The universe appears resistant to connection, not hostile to it. That distinction matters. Hostility implies impossibility. Resistance implies difficulty. The difference is profound. Mountains resist travel. They do not forbid it. Oceans resist exploration. They do not forbid it. The cosmos resists communication. It does not necessarily forbid it. Future generations may discover methods humanity has not yet imagined. New observational techniques, new forms of communication, new approaches to long-term survival. The story remains unfinished. And perhaps that is the most important conclusion of all. The silence is not the end of the story. The silence is the current chapter. A chapter being written by a young technological civilization orbiting an ordinary star in a spiral arm of the Milky Way. A civilization that has only recently begun listening, only recently begun searching, only recently begun understanding the scale of the challenge before it. From the perspective of cosmic history, humanity has barely arrived. We are newcomers asking ancient questions. The universe has existed for billions of years. Our search has lasted only decades. Perspective matters. Patience matters. Time matters. Perhaps somewhere beyond the darkness, another civilization once asked the same questions. Perhaps another asks them now. Perhaps others will ask them millions of years from today. The universe may be filled with separate histories unfolding in parallel, histories rarely intersecting, histories occasionally overlapping, histories connected by the same curiosity, the same desire to understand, the same impulse to look upward. And so we arrive at the final reflection. Maybe the universe is built to keep civilizations apart, not through intention, not through design, but through the natural consequences of distance, time, and the laws of physics. Yet if that is true, then every civilization faces the same challenge: to endure, to preserve knowledge, to remain curious, to continue searching despite uncertainty. The silence does not tell us that the story is over. It tells us that the story is still being written across centuries, across millennia, across interstellar distances, throughout the galaxy. And perhaps one day, somewhere in that immense future, two distant histories will finally meet. Until then, the stars remain silent, and humanity continues listening.